Hello there, and welcome to Science for Sleep, where curiosity slows down, softens its edges, and science becomes something you can gently drift alongside. Tonight, we're setting our gaze on something familiar, something that has followed you quietly for your entire life, rising and falling without asking for attention, glowing softly without making a sound, the moon. It's been there on late walks, on quiet drives, on evenings when the sky feels just a little too big. It's easy to think of it as harmless, a steady companion, a distant light that simply watches. But what if that calm presence is a little misleading? Because beneath that soft glow lies a world that is anything but gentle, a place where silence isn't peaceful, where stillness isn't safe, and where even standing still can slowly put you in danger. The moon looks quiet from here, but it is not a quiet place. Before we ease into that thought, I'd like to ask you something simple. Where are you listening from tonight, and what does the moon look like where you are right now? Is it high and bright, or hidden somewhere behind clouds, or perhaps not visible at all? It's interesting, isn't it, that something so far away can still feel so present in our daily lives. And if this journey feels calming, or just gives your mind something gentle to follow as you wind down, you can always leave a like or subscribe. It helps this quiet little space reach others who might need a slower moment too. Now, without rushing, let's begin with the moon as we usually think of it. Not as a place, but as a feeling. For most of us, the moon doesn't feel dangerous at all. If anything, it feels comforting. There's a reason it appears in lullabies, in stories told to children, in poems and quiet songs. It's associated with calm nights, soft light, and a kind of steady presence that doesn't demand anything from you. Unlike the sun, which can burn, blind, and overwhelm, the moon seems gentle. It reflects light instead of producing it. It rises slowly. It doesn't rush across the sky. It doesn't make noise. It doesn't interfere. It simply appears. And because of that, we tend to think of it as safe, almost passive, something that exists more for observation than for interaction. But that perception is built entirely from distance. From here, the moon is about 384,000 kilometers away. That's far enough that all of its sharper edges, all of its harsher conditions, are softened into something smooth and quiet. It's like looking at a mountain from far away. From a distance, it looks calm, even inviting. But up close, it's steep, rough, unpredictable. The moon is very similar. If you were standing on its surface right now, the first thing you would notice isn't beauty. It's absence. No air, no sound, no movement except your own. There's no breeze, no rustling, no distant hum of anything alive. The kind of silence that isn't just quiet, but complete. The kind that makes you aware of every small movement you make, because nothing else exists to fill the space. And that silence isn't peaceful in the way we experience it on Earth. Here, silence is usually temporary. It sits between sounds. On the moon, silence is permanent. There is nothing to break it. Without an atmosphere, there's also no protection. On Earth, the air around you does more than just let you breathe. It shields you. It softens temperature changes. It burns up small objects before they reach the ground. It filters radiation. The moon has none of that, which means that even standing still there, doing nothing at all is not safe. Temperature alone becomes a problem almost immediately. On Earth, temperatures shift gradually. Even on a hot day or a cold night, the air helps regulate the change. But on the moon, there is no air to carry heat or distribute it. So when sunlight hits the surface, it becomes extremely hot. Around 127 degrees Celsius, hot enough to cause serious damage in a very short amount of time. But step into shadow and the opposite happens. Temperatures can drop to minus 173 degrees Celsius, a difference so extreme that materials expand and contract rapidly, surfaces crack, and anything exposed struggles to remain stable. And these changes don't happen over long seasons. They happen simply by moving from sunlight into shadow. Now imagine being there, trying to move, trying to work, trying to survive, while every step could take you from one extreme into another. Even something as simple as standing in the wrong place at the wrong time becomes dangerous. Then there's the ground beneath your feet. From here, the moon looks smooth, pale and even, but up close it's covered in a layer of dust that behaves in a very unusual way. This dust, called regolith, isn't like the dust you're used to. It's not soft or rounded, it's sharp. Every particle is jagged, because there's no wind or water to wear it down over time. On Earth, grains of sand become smooth, because they tumble, collide, and erode. On the moon, nothing moves unless something forces it to, so the dust stays rough, almost like tiny shards of glass. And it clings to everything. It sticks to suits, to equipment, to surfaces. It gets into joints, into seals, into places it shouldn't be. And because it's so fine and sharp, it can slowly wear things down. During the Apollo missions, astronauts noticed that lunar dust caused problems almost immediately. It scratched visors, damaged equipment, and even caused irritation when it came into contact with skin. And that was during short visits. Imagine living there. Even walking becomes something you have to think about carefully. Not because it's difficult, but because it's different. The moon's gravity is only about 1/6 of Earth's. That sounds helpful at first. Lighter steps, easier movement. But it changes how your body behaves. You don't walk the same way. You bounce slightly. You drift more than you expect. And stopping becomes just as important as starting, because momentum carries you further. It's easy to underestimate how much your body relies on Earth's gravity. Every movement you make is tuned to it. Take that away, or reduce it significantly, and suddenly even simple actions require adjustment. Over time, that becomes a risk. Muscles weaken, bones lose density. The body begins to change because it's no longer working against the same force it evolved with. And all of this is happening in an environment where there is no immediate help, no natural resources to fall back on, no easy way to correct mistakes. The moon doesn't forgive errors. Even something as small as a damaged suit, a missed step, or a moment of distraction can become serious very quickly. And yet, from here, it still looks calm. That contrast is what makes the moon so interesting. It appears gentle because we experience it from a distance. We see the light, not the conditions that produce it. It's a bit like watching waves from the shore. From far away they look slow, rhythmic, almost relaxing. But step into them and you realize there's strength there. Movement that can push, pull, and overwhelm if you're not careful. The moon is like that. It doesn't move quickly. It doesn't demand attention. It doesn't announce its dangers loudly. But they are there, built into its very nature. And that's before we even begin to consider the things that don't come from the moon itself, but from everything around it. Because space isn't empty in the way we often imagine. It's active. It's filled with radiation, with tiny fragments of rock moving at incredible speeds, with forces that are constantly interacting with anything exposed to them. On Earth, we are protected from most of this. The atmosphere absorbs it. The magnetic field deflects it. We live inside layers of protection we rarely think about. The moon has almost none of those layers, which means that anything on its surface is directly exposed. And that exposure introduces another kind of danger, one that you can't see, can't feel immediately, but that builds over time, radiation. But we'll move into that slowly because, like everything else about the moon, it's not something that announces itself clearly. It doesn't make noise. It doesn't change the sky. It simply exists, quietly, constantly, waiting for anything unprotected to cross its path. If you think about it for a moment, it's quite curious how easily the moon earns our trust. It doesn't flicker unpredictably. It doesn't roar like a storm or blaze like the sun. It doesn't demand attention in a way that feels urgent. Instead, it just appears, night after night, keeping a kind of quiet consistency that feels reassuring almost by default. That consistency matters more than we usually realize. As humans, we tend to associate predictability with safety. Things that behave in expected ways feel less threatening. A ticking clock, a familiar road, a routine evening. Even if those things aren't inherently safe, they feel manageable, because we understand them. And the moon fits perfectly into that category. It rises, it sets, it changes shape in a cycle we've known for thousands of years. Full, half, crescent, and then back again. There's no surprise to it. No sudden shift that makes you stop and question what's happening. You can look up at it and feel like you know it. But that feeling isn't built on experience. It's built on distance. Because everything we think we understand about the moon comes from observing it safely from Earth, wrapped in layers of protection we almost never think about. Air, gravity, magnetic shielding, temperature regulation. These are things that quietly stand between us and the true nature of space. So when we look at the moon, we're not seeing it as it is, we're seeing it filtered through safety. And that creates a kind of illusion. It's similar to how a fire looks from across a room, contained, controlled, even pleasant. You might sit near it, enjoy the warmth, watch the light flicker, but the closer you get, the more you understand that the calm appearance hides something very different. The moon works the same way, just on a much larger scale. Part of what reinforces this illusion is the kind of stories we tell about it. For most of human history, the moon hasn't been described as dangerous. It's been described as watchful, mysterious, sometimes romantic, sometimes symbolic. It shows up in lullabies, guiding travellers through the night. It appears in myths as a quiet observer, not an aggressor. Even when it's associated with strange behaviour, like the idea of lunacy or full moon restlessness, the moon itself isn't portrayed as hostile. It's more like a passive influence, something that nudges rather than harms, and that subtle difference shapes how we think about it. We don't grow up learning to fear the moon, we grow up learning to notice it. A child sees the moon and points, an adult glances at it and moves on. It becomes part of the background, like a familiar landmark that doesn't need explanation anymore. And once something becomes background, we stop questioning it. But there's another reason the moon feels harmless, and it has to do with scale. The moon looks small, not tiny, but manageable. It fits neatly into the sky. You can cover it with your thumb if you hold your hand out far enough. It doesn't dominate your view the way the sun does. It doesn't overwhelm your senses. It feels distant, but also contained. That visual experience makes it easy to underestimate. In reality, the moon is over 3,400 kilometers in diameter. That's roughly a quarter the size of Earth. If you could stand close to it, it wouldn't feel small at all. It would feel vast, stretching far beyond your line of sight in every direction. But from here, it's reduced to something you can glance at between thoughts, and that reduction changes how we interpret it. There's also the way light behaves. The moon doesn't produce its own light. It reflects sunlight, which softens everything about its appearance. The brightness is gentle, diffused, never harsh enough to hurt your eyes. That softness carries an emotional weight. Bright light can feel aggressive. Dim, cool light feels calm. So even though the moon is illuminated by the same sun that can burn skin and damage eyes, the way that light reaches us is completely different. Filtered, reduced, tamed. And because of that, we associate it with calmness rather than intensity. Even the colour contributes to the illusion. The moon often appears pale, sometimes slightly golden, sometimes bluish depending on the atmosphere. These are not colours we associate with danger. Danger tends to be sharp, red, bright, sudden. The moon is none of those things. It is slow, and slowness feels safe. If something moves quickly, we pay attention. Fast motion suggests urgency, unpredictability, potential harm. But the moon moves so gradually that you can watch it for minutes and barely notice a change in position. It drifts, it doesn't rush. And that steady, almost imperceptible movement reinforces the idea that it's not something to worry about. But this is where perception begins to separate from reality. Because the moon is not inactive. It is constantly moving, orbiting Earth at about 3,700 kilometers per hour. That's faster than most aircraft, faster than anything we casually experience. We just don't feel it. And when we don't feel something, we tend to ignore it. The same applies to its influence. The moon is strong enough to move entire oceans. Tides rise and fall because of its gravitational pull. Massive bodies of water shift across the planet in response to its presence. And yet, standing on a beach, that movement feels gentle, rhythmic, almost soothing. It doesn't feel like a force capable of reshaping coastlines over time. It doesn't feel like something powerful. It feels like a pattern. And patterns, again, feel safe. There's a kind of quiet assumption built into all of this. If something hasn't harmed us before, it probably won't. If it has always been there, behaving in the same way, then it must be stable. But that assumption depends entirely on context. The moon has never harmed us directly because we have never truly been exposed to it. We've always been separated by distance and protected by Earth. Take away that separation, and the situation changes completely. Imagine for a moment that you're no longer observing the moon from Earth. You're standing on its surface. There's no atmosphere, no sound, no buffer between you and the environment. The same object that looked calm from a distance now surrounds you, and suddenly the illusion fades. That soft light becomes direct, unfiltered sunlight. That steady presence becomes a landscape of extremes. That quiet companion becomes an environment where survival depends on constant attention. The moon doesn't change, your position does. And that's the key to understanding why it feels harmless. It's not that the moon is safe, it's that we are safe from the moon. There's a subtle but important difference there. We tend to think of safety as a property of objects or places. Something is either safe or dangerous. But in reality, safety is often about the relationship between you and that thing. A deep ocean is safe if you're on a boat. Dangerous if you're in the water without support. A fire is safe in a fireplace. Dangerous if you're too close. The moon is safe because we are far away, protected. Observing rather than interacting. And because that distance has always been there, it's easy to forget that it's doing all the work. There's also the matter of familiarity over time. Humans have been watching the moon for as long as we've existed. It has been a constant presence in the sky, unchanged in any noticeable way. Generations have passed beneath it without seeing it behave differently. That kind of long-term consistency builds trust. We assume that something so stable must be benign, but stability doesn't equal safety. It just means predictable. A perfectly still environment can still be hostile. A place that never changes can still be dangerous if the conditions are extreme. And the moon is exactly that. Stable, predictable, and completely unforgiving. Interestingly, even when we did start visiting the moon during the Apollo missions, the way those missions were presented didn't fully disrupt the illusion. We saw astronauts walking, bouncing lightly, planting flags. The images were calm, almost playful. The slow-motion movement made everything look gentle, even enjoyable. But those images didn't show the underlying risk. They didn't show the constant awareness required to avoid mistakes. They didn't show how quickly things could go wrong if a system failed, if a seal broke, if something unexpected happened. They showed success, and success tends to smooth over danger. It creates a narrative where things feel controlled, even when they are not. So the illusion remained. The moon continued to feel like a place we could visit, explore, maybe even live on someday without too much concern. But that perception is slowly changing. As we learn more about the moon, as we study its surface, its conditions, its history, a different picture begins to emerge. Not dramatic, not alarming in a sudden way, but steadily more detailed, more real. And that reality includes risks that are easy to overlook if you're only thinking about how the moon looks from here. Because what we see is only one version of it, a distant version, a filtered version. And as we move forward, as humans consider returning to the moon, building there, staying there longer than ever before, that illusion becomes something we have to let go of. Because understanding the moon as it truly is means looking past the calm surface and paying attention to the details that don't show up in a glance. Details like the environment itself, the kind that doesn't just feel different, but actively works against you in ways that are easy to underestimate at first. The moment you begin to think about the moon without the comfort of distance, one detail stands out almost immediately. There is no air. Not thinner air, not colder air, not unfamiliar air, none at all. And it's easy to underestimate just how important that is because air is something you never have to think about on Earth. It's always there, quietly doing its job. You don't wake up and check if it's still around. You don't plan your day around whether you'll be able to breathe. It simply exists, and because of that, it becomes invisible in the way we think about the world. But the absence of air changes everything. If you were suddenly placed on the moon without protection, the problem wouldn't be subtle or gradual. It would be immediate. Within seconds, your body would begin to react to the vacuum. Not dramatically in the way films often show, but decisively. You wouldn't be able to breathe, of course. That part's obvious. But beyond that, the pressure difference would begin to affect your body in ways that are less familiar. Gases dissolved in your bloodstream would start to form bubbles. Moisture on your skin and in your eyes would begin to evaporate. Your body is built for an environment where pressure exists. Take that away, and systems that normally operate quietly begin to struggle. And yet, even that description doesn't fully capture the scale of the problem because air is not just about breathing. It is one of the most important protective layers you have. On Earth, the atmosphere acts like a shield. It absorbs radiation, slows down incoming objects, spreads heat, carries sound, and regulates temperature. It connects everything. Without it, the environment becomes fragmented, isolated. On the moon, nothing is carried from one place to another, unless something physically moves it. There is no wind, no weather, no clouds, no gradual transition between conditions. If you step from sunlight into shadow, there is no air to soften that change. The temperature doesn't ease from warm to cool, it drops sharply because there's nothing to hold on to the heat. Air on Earth acts like a buffer. It stores energy and releases it slowly. That's why evenings cool down gradually rather than instantly. That's why shade feels refreshing instead of extreme. Remove that buffer and everything becomes more abrupt, more direct. The moon is a place of direct exposure. And that exposure creates a kind of silence that goes beyond what we usually mean when we say something is quiet. Because sound needs a medium to travel through. On Earth, that medium is air. Vibrations move through it, reach your ears, and become what you recognize as sound. On the moon, there is no medium. If you were standing there and something happened nearby, a rock shifting, a tool dropping, even an explosion, you wouldn't hear it in the way you expect. The vibrations wouldn't travel through empty space to reach you, unless something is directly connected to you, touching your suit, your body, your equipment. There is nothing to carry the sound. That means the moon is not just quiet, it is completely silent. And that kind of silence is different from anything you experience on Earth. Even in the quietest place you can think of, there is always some background presence. A distant hum, a faint movement of air, something subtle that reminds you the world is still active around you. On the moon, that disappears. The only sounds you would hear are the ones created inside your own system. The movement of your suit, your breathing, the faint mechanical noises of whatever equipment is keeping you alive. Everything else is still. And while that might sound peaceful at first, it introduces another kind of challenge. Because sound is one of the ways we understand our surroundings. You hear something before you see it. You notice changes in your environment through subtle shifts in noise, footsteps, movement, distant activity. Without sound, your awareness becomes more limited. You rely entirely on what you can see and what you can physically feel, and that can be disorienting. It changes how you move, how you react, how you interpret what's happening around you. Even communication becomes more complicated. On Earth, speaking is simple. Air carries your voice. Words travel naturally. On the Moon, there is no such connection. You can't simply call out to someone nearby. Your voice has nowhere to go. Communication depends entirely on technology. Radios, signals, systems that translate vibrations into something that can be transmitted. If those systems fail, even briefly, you're cut off. Not just from distant support, but from anyone standing just a few meters away. Two people could be facing each other, separated by only a small distance, and without functioning equipment, they would not be able to speak. That kind of isolation is easy to overlook until you imagine being in it. Now consider something else that air does quietly, constantly. It protects you from what's above. Space is not empty in the way we often think. It's filled with radiation, with particles travelling at high speeds, with energy that moves freely because there is nothing to stop it. On Earth, the atmosphere absorbs a large portion of that. It acts like a filter, reducing the amount of harmful radiation that reaches the surface. The Moon has no such filter. Anything coming from space reaches the surface directly. That includes solar radiation from the Sun, as well as cosmic radiation from much deeper parts of the universe. High-energy particles that can pass through materials, interact with cells, and cause damage over time. You wouldn't feel it happening. There's no immediate sensation that tells you something is wrong. But the exposure is constant, and without protection, it accumulates. This is one of the reasons astronauts need specially designed suits and shielding, not just for breathing, not just for temperature, but for protection against something you cannot see or sense in the moment. The absence of air removes that invisible barrier. It turns space from something distant into something immediate. Then there's the matter of incoming objects. On Earth, small meteoroids enter the atmosphere regularly. Most of them burn up before they reach the ground. The friction with the air generates heat, causing them to disintegrate. That's why shooting stars appear briefly and then vanish. On the Moon, there is no atmosphere to create that friction. Even very small objects can reach the surface at high speeds. Tiny particles, moving fast enough to cause damage on impact, you wouldn't see most of them. They're too small, too fast. But they are there, constantly arriving. Over time they shape the surface. They create the fine dust that covers everything. They add to the countless small impacts that have been happening for billions of years. And if you're there, unprotected, those same particles become a direct risk. Again, not dramatic, not something you would necessarily notice in a single moment, but part of an environment where nothing is filtered, nothing is softened. Everything reaches you directly. It's interesting how many of these effects come back to the same point. Air is not just something we breathe. It is a system that connects, protects, and stabilizes everything around us. It carries heat, sound, and energy. It slows things down. It creates gradients instead of extremes. It allows for communication, for awareness, for subtle interaction with the environment. Remove it, and all of those functions disappear. The Moon becomes a place where everything is isolated. Heat stays where it is. Sound doesn't travel. Radiation passes through. Objects arrive without warning, and you standing there are exposed to all of it. There's no gentle transition into this environment, no gradual adjustment. It is immediate. And yet, from Earth, none of that is visible. You don't see the absence of air when you look at the Moon. You see light. You see shape. You see a surface that looks smooth and quiet. The most important difference is invisible, which is why it's so easy to overlook. But once you start to think about it, once you begin to imagine what it means to exist in a place without air, the Moon becomes something else entirely. Not a distant object to observe, but an environment defined by absence. And that absence doesn't just make things different, it makes them more extreme. Because without air to connect and soften everything, the moon doesn't moderate anything at all. It's one thing to imagine a place without air. It's another to understand what that actually does to temperature. On Earth, temperature feels gradual. Even when it changes quickly, there's still a sense of transition. Morning warms into afternoon. Afternoon cools into evening. You step into shade and it feels a little cooler, not drastically different. That sense of smooth change comes from the atmosphere. Air absorbs heat, stores it, and moves it around. It spreads warmth from one place to another, softens extremes, and creates a kind of balance that we rarely question. But on the moon, there is no such balance. Without air, there is nothing to hold heat and nothing to distribute it. Energy from the sun hits the surface directly, and whatever it touches heats up quickly. Whatever it doesn't touch remains cold. There is no in-between. If you were standing on the moon during its daytime, the ground beneath you could reach around 127 degrees Celsius. That's hotter than boiling water, hot enough to damage equipment, degrade materials, and become dangerous very quickly without proper protection. And yet, just a short distance away, in shadow, temperatures can drop to minus 173 degrees Celsius. That's not a seasonal difference. That's not something that happens over days or weeks. That difference exists at the same time, depending entirely on whether sunlight is reaching a surface. Imagine standing at the edge of a shadow, 1 foot in sunlight, 1 foot in darkness. The difference between those two positions is not subtle, it's extreme. On Earth, even deserts, which are known for large temperature swings, don't behave this way. A desert might be hot during the day and cold at night, but those changes still follow a cycle. Heat builds, then slowly escapes. On the moon, there is no air to slow that process down. Heat arrives quickly, and it leaves just as quickly. That creates an environment where temperature isn't something stable, it's something that depends entirely on your position and timing. Even the length of a day on the moon contributes to this effect. A single lunar day, meaning one full cycle from sunrise to sunrise, lasts about 29.5 Earth days. That means that once the sun rises over a particular location on the moon, it stays in the sky for about 2 weeks. 2 weeks of continuous sunlight, 2 weeks of continuous heating. Then, when the sun sets, that same location enters 2 weeks of darkness, 2 weeks of continuous cooling. There is no rapid cycle to balance things out, no regular alternation between light and dark every 24 hours. Instead, each phase lasts long enough for temperatures to reach their extremes. During those long days, surfaces absorb solar energy with nothing to stop it. Temperatures climb and remain high for extended periods. Materials expand, surfaces become intensely hot, and anything exposed must be designed to handle it. Then, during the long night, all that heat radiates away into space, and because there is no atmosphere to trap it, it doesn't linger, it disappears. Temperatures fall, and they keep falling until they reach levels that are difficult to imagine in everyday experience. Now consider what that means for anything trying to exist there. Every structure, every tool, every system must handle both extremes, not just heat, not just cold, but both, repeatedly, over long periods. Expansion and contraction become constant challenges. Materials that work well at one temperature may become brittle at another. Seals can weaken, surfaces can crack. Mechanical systems must account for changes that would be insignificant on Earth, but become critical in such conditions. Even something as simple as moving between areas can become complicated. If you leave a sunlit region and enter shadow, you're not just stepping into a cooler space. You're stepping into a completely different thermal environment, and your equipment must adjust immediately. There's no gradual cooling, no time to adapt. It's instant. The same applies in reverse. Moving from shadow into sunlight exposes you to intense heat without any buffer. That constant shift requires careful planning. On Earth, we take for granted how forgiving our environment is. You can walk from indoors to outdoors, from sunlight to shade, and your body adjusts. The air helps regulate the change. Clothing helps moderate it further. On the moon, your suit becomes your entire environment. It must maintain a stable internal temperature regardless of what's happening outside. It must protect you from both overheating and freezing, often within the same general area. And if that system fails, even briefly, the consequences are immediate. This is where the moon's temperature becomes more than just a physical condition. It becomes a constant pressure on everything you do. Every movement, every decision, every path you take must account for where the sun is and how it affects your surroundings. You don't just think about where you're going. You think about whether that place is in light or shadow, and what that means for the next few minutes, the next few hours. There's also something else that makes these temperature extremes particularly challenging. They are invisible. On Earth, you can often see signs of temperature. Heat creates shimmer in the air, cold creates frost, breath, condensation. There are visual cues that help you anticipate what you're about to experience. On the moon, there are no such indicators. A shadow looks like a shadow. A sunlit area looks bright. But the difference between them is far greater than anything your eyes can tell you. That lack of visual feedback means you rely entirely on knowledge and instrumentation. You need to know where it is safe to step, where it is safe to remain, how long you can stay in a particular place before conditions become too extreme. It turns something simple, like walking across a surface, into something that requires constant awareness. Even the timing of activities becomes critical. If you're working on the moon, you need to plan around the long day and long night. Certain tasks may only be possible during specific phases. Energy systems must store power during sunlight and operate during darkness. Thermal management becomes a continuous process, not just for people, but for everything operating there. Then there's the effect on the surface itself. The repeated heating and cooling over long periods causes stress in the lunar material. Rocks expand during the day and contract at night. Over time, this leads to cracking and fragmentation. This is one of the reasons the moon's surface is covered in fine dust. The extreme temperature cycles break down larger rocks into smaller particles. And those particles, as we mentioned earlier, don't smooth out over time. They remain sharp. So the temperature extremes don't just affect what's there now. They shape the environment itself. They create the conditions that make the moon's surface what it is. A place where everything is exposed, everything is affected, and nothing is moderated. It's interesting how all of this connects back to something so simple. The absence of air. Without it, there's no medium to hold heat, no system to distribute energy, no gradual transition between conditions. Everything becomes direct, and that directness makes the moon an environment of contrasts. Bright and dark, hot and cold, sunlight and shadow, each one defined not by subtle differences but by extremes. From Earth, the moon looks calm, its light is steady, its surface appears unchanged. It doesn't give any indication of the conditions that exist there. But once you begin to think about it in terms of temperature, once you imagine standing on that surface and experiencing those shifts, the calm appearance starts to feel a little misleading. Because nothing about those conditions is gentle. They are precise, predictable, and completely unforgiving. And they don't require anything dramatic to become dangerous. All it takes is being in the wrong place at the wrong time, standing where the sun reaches too long, or stepping into shadow without preparation. It's a reminder that danger doesn't always come from movement or sudden change. Sometimes it comes from stability, from conditions that remain consistent long enough to reach their limits. And on the moon, those limits are reached more easily than you might expect. Once you begin to picture the moon as a place you could actually stand, rather than something you simply look at, the details start to shift in a subtle way. It's no longer just about light and distance, it becomes about the surface itself. And at first glance, that surface doesn't seem especially threatening. It looks pale, smooth in places, slightly uneven in others. You might imagine it feeling like dry sand or fine powder, something soft enough to step into without much concern. But that impression doesn't last very long. because the moon's surface is covered in something that behaves very differently from anything you've likely experienced before. A layer of dust that isn't really dust in the way we understand it on Earth. It's called regolith, and it covers nearly the entire surface. In some areas, it's just a few centimetres deep. In others, it can reach several metres. It's the result of billions of years of impacts, constant bombardment by tiny meteoroids breaking down rocks into smaller and smaller fragments. But what makes it unusual isn't just how it forms, it's how it feels, how it behaves, and how it interacts with everything around it. On Earth, dust and sand are shaped by wind and water. Over time, particles collide, tumble, and wear down. Edges become rounded, surfaces become smoother. Even the finest grains have been softened by constant motion. The moon doesn't have wind. It doesn't have flowing water. Nothing moves unless something forces it to. So the particles remain sharp. Each tiny grain is jagged, irregular, almost like microscopic shards. Not polished, not softened, but fractured. Broken in ways that leave edges intact. And those edges matter, because they change how the dust interacts with surfaces, with equipment, and with anything that comes into contact with it. Imagine picking up a handful of something that looks like fine powder, only to find that it behaves more like a collection of tiny cutting surfaces. It doesn't flow as smoothly. It doesn't slide away easily. It grips, and that's where the problem begins. During the Apollo missions, astronauts encountered this dust almost immediately. At first, it seemed manageable. It coated their boots, clung lightly to their suits, followed them as they moved. But as time passed, its behaviour became more noticeable. It didn't fall off easily. It stuck, not just loosely, but persistently, as if it were drawn to surfaces. Part of this is due to static electricity. The moon's surface can become electrically charged, especially under sunlight. That charge causes the dust to cling more strongly than you would expect. So instead of brushing away, it lingers. It collects in folds, in joints, in seams. And because it's so fine, it finds its way into places that are difficult to clean. Over time, this becomes more than just an inconvenience. It becomes a form of wear. Those sharp particles begin to scratch surfaces. Visors become slightly hazy. Seals experience friction. Moving parts don't glide as smoothly as they should. It's not immediate damage. It doesn't happen all at once, but it accumulates. A slow, steady process of degradation. And because everything on the moon depends on equipment functioning correctly, even small changes can matter. A slightly scratched visor reduces clarity. A worn seal may not close as tightly. A joint that doesn't move smoothly requires more effort, more energy, more attention. Each of these on its own might seem minor, but together they create a system that becomes less reliable over time, and reliability in that environment is essential. There's also something else that makes lunar dust particularly difficult to deal with. It doesn't behave like Earth dust when disturbed. On Earth, if you kick up dust, it rises briefly and then settles. Air resistance slows it down. Gravity pulls it back gradually. On the moon, there is no air to slow it. So when dust is disturbed, it follows a different path. It moves in clean arcs, rising and falling without the soft drifting motion we're used to. It doesn't swirl. It doesn't hang in the air. It simply moves and settles. That might sound simpler, but it creates its own challenges. Because without air, there's nothing to carry particles away or disperse them. They land exactly where their motion takes them. And if that motion brings them toward you, toward your equipment, toward critical surfaces, they stay there. There's no breeze to clear them, no natural process to remove them. Everything that lands stays. Now consider what happens when that dust is brought inside a controlled environment. During the Apollo missions, when astronauts returned to their lunar module, some of that dust came with them. It clung to their suits, their boots, their tools. Inside the module, it became noticeable very quickly. The particles floated briefly before settling, and because they were so fine, they could be inhaled. And this is where another concern appears. lunar dust is not just sharp externally, it can be harmful internally. The particles are small enough to enter the respiratory system, and their jagged structure means they don't behave like typical dust in the lungs. On Earth, many particles are rounded or softened, making them less likely to cause irritation at a microscopic level. Lunar dust, by contrast, can remain abrasive. It can irritate tissue, potentially causing inflammation over time. The astronauts reported a kind of reaction to it, sometimes described as similar to hay fever, irritation in the eyes, throat, and nose, and that was after relatively short exposure. Long-term exposure would present a more serious concern, which means that managing dust isn't just about keeping equipment clean, it's about maintaining a safe living environment. Preventing contamination becomes a continuous task. Every entry, every exit, every movement across the surface introduces the possibility of bringing more dust into places where it can cause problems. And because it's so persistent, removing it completely is extremely difficult. There's also the way it affects visibility and perception. A thin layer on a visor can reduce clarity just enough to matter. A slight haze can change how you interpret distance, how you judge surfaces, how you move. On Earth, we rely heavily on visual cues to navigate. Anything that interferes with that, even slightly, can increase risk. On the Moon, where the environment is already unfamiliar, that added layer of uncertainty becomes significant. Then there's the interaction between dust and temperature. Because the particles are exposed directly to sunlight and shadow, they experience the same extremes as the surface. They heat up quickly, they cool down just as quickly, and when they come into contact with equipment, they transfer that heat or cold. So dust isn't just a passive layer, it becomes part of the thermal environment. It contributes to how heat is absorbed, retained, and transferred. And that adds another level of complexity to managing conditions on the Moon. What's interesting is how something so small can have such a wide range of effects. Individually, each particle is almost insignificant, but together they form a layer that covers everything, a layer that interacts with light, with heat, with movement, with systems designed to function in a precise way. And because it's always there, always present, it becomes part of every activity. You can't step onto the Moon without interacting with it. You can't move without disturbing it. You can't avoid it. From Earth, none of this is visible. The Moon looks clean, smooth in some areas, textured in others, but not dangerous. Certainly not something that could cause problems on such a small scale, but that's the nature of this particular hazard. It doesn't rely on size or force, it relies on persistence, on being everywhere, all the time, quietly interacting with anything that comes into contact with it. And that makes it easy to underestimate, because when we think of danger, we often imagine something large, something immediate, something obvious. Lunar dust is none of those things. It's subtle, it builds slowly, it works in the background, and by the time its effects become noticeable, it's already been there for a while. Which is why understanding the Moon means paying attention not just to the big, visible conditions, but to the small, consistent ones as well. The ones that don't announce themselves but remain constant. Because those are often the ones that shape the experience the most. And as you continue to imagine being there, moving across that surface, adjusting to the environment, there's another factor that begins to stand out. There's something about the idea of low gravity that feels almost playful at first. You've probably seen it before. Footage of astronauts moving in slow bouncing steps, drifting slightly higher than expected, almost as if they're moving through a softer version of reality. It looks easier, lighter, less effort, and compared to Earth, it is. The Moon's gravity is about 1/6 of what you're used to. If you weigh 60 kilograms on Earth, you would feel like you weigh only about 10 kilograms there. Every step requires less force. Every movement feels less restricted. At a glance, that sounds like an advantage. Less strain on the body, easier lifting, greater mobility. But as with many things on the Moon, What seems helpful at first has a way of introducing complications the longer you think about it. Because gravity isn't just something that holds you down. It's something your entire body relies on to function normally. Every movement you make is calibrated to it. Every step you take, every shift in balance, every small adjustment your muscles perform happens with Earth's gravity as a constant reference. Remove most of that force, and those calibrations no longer apply. You don't just feel lighter, you move differently in ways that take time to understand. Walking, for example, is no longer quite the same. On Earth, your steps are controlled by a predictable cycle. You lift your foot, move it forward, place it down, and your weight transfers smoothly. On the Moon, that pattern changes. With less gravity pulling you down, each push off the ground sends you slightly higher and farther than expected. Instead of walking, you tend to move in a kind of slow, hopping motion. A series of small, controlled jumps. It looks simple, but controlling that motion requires attention. Because once you're moving, stopping isn't immediate. Momentum carries you. On Earth, friction and gravity work together to bring you to a stop quickly. On the Moon, with less force pulling you downward, you glide a bit longer. You travel farther than you intended. That means every movement has to be planned more carefully. If you push too hard, you don't just take a bigger step, you overshoot. And in an environment where the ground is uneven, covered in dust and filled with small obstacles, overshooting can lead to falls. Falling itself behaves differently too. With lower gravity, you fall more slowly, which might seem safer. There's more time to react, more time to adjust your position. But the impact is still real, and because you're often moving with momentum in a direction you didn't fully intend, the way you land can be unpredictable. Recovering from a fall becomes more complicated, especially when you're wearing a suit that restricts movement. Even standing back up requires effort and coordination. Now consider what happens over longer periods. Your body is designed to work against gravity. Muscles maintain strength by resisting it. Bones maintain density because they bear weight. Take that resistance away, and the body begins to change. Muscles weaken because they're not being used in the same way. Bones lose density because they're not supporting the same load. This isn't something you notice immediately. It happens gradually. But over time, the changes become significant. Astronauts who spend extended periods in low-gravity environments, like the International Space Station, experience these effects. Even with regular exercise, muscle mass decreases and bone density can decline. On the Moon, the gravity is stronger than in orbit, but still much lower than on Earth, so the same processes would occur just at a different rate. That means that living there long-term would require constant effort to maintain physical health. Exercise wouldn't be optional, it would be necessary, and even then, it might not fully counteract the effects. There's also the matter of coordination. Your sense of balance is closely tied to gravity. Your inner ear uses it as a reference point to understand orientation. Which way is up, which way is down. Reduce that reference and your perception changes. Movements that feel natural on Earth can feel slightly off. Your body has to relearn how to interpret motion. This can lead to moments of disorientation, not dramatic, not overwhelming, but enough to affect how you move, how you react, how you judge distances and timing. And in an environment where precision matters, even small misjudgments can have consequences. Then there's the way objects behave. It's not just your body that feels lighter. Everything does. Tools, equipment, materials. That can make lifting easier, but it also changes how things move once they're in motion. If you push something, it doesn't settle quickly, it keeps going. If you drop something, it falls more slowly, but it can bounce or slide in ways that are less predictable. And because there's no air resistance, nothing slows it down except contact with another surface. That means that even simple tasks like placing tools or moving equipment require more attention. You have to think about where things will go after you let go of them, because they don't behave quite the way you expect. There's also an interesting effect on effort. At first, moving in low gravity can feel easier, less force required, less strain on muscles, but over time it can become tiring in a different way because you're constantly adjusting, constantly correcting for movements that don't behave as expected. It's not the same kind of fatigue you feel on Earth. It's more about coordination, about maintaining control in an environment that doesn't respond in familiar ways, and that can build up, especially when combined with everything else the Moon demands. Then there's the psychological aspect. Moving in low gravity feels unfamiliar enough that it changes your sense of presence. On Earth you feel grounded. Literally, there's a constant connection between you and the surface beneath you. On the Moon, that connection is weaker. You're still standing, still in contact with the ground, but the sensation is different, less firm, less anchored, and that can subtly affect how you perceive your environment. There's a slight sense of floating, even when you're standing still. A reminder that the rules you're used to don't fully apply, that you're in a place where even something as basic as gravity behaves differently. All of this adds up to a kind of quiet challenge. Low gravity doesn't present itself as an obvious danger. It doesn't make noise. It doesn't create immediate discomfort. In fact, it can feel almost enjoyable at first. But it changes the way you move, the way your body functions, the way objects behave, and the way you interact with your surroundings. And those changes require constant awareness. Because without that awareness, it's easy to make small mistakes, to move a little too quickly, to push a little too hard, to misjudge a distance or a landing. And on the Moon, small mistakes don't always stay small. They can lead to situations that are difficult to correct, especially when everything else, the environment, the dust, the temperature, is already working against you. It's interesting how something that seems like a benefit can become a complication. Less gravity sounds easier, but easier doesn't always mean safer. Sometimes it just means different. And different requires adjustment, which is something the Moon demands in almost every aspect. At this point, the Moon might already feel a little less calm than it did at the beginning, not because anything about it has changed, but because you're starting to see what has always been there, just from a different perspective. And now we arrive at something that is even harder to notice, because unlike temperature, unlike dust, unlike gravity, this is something you cannot see, cannot feel in the moment, and cannot easily sense without instruments. Radiation. It's always there, quiet, constant, and moving through space without interruption. On Earth, this isn't something you think about very often, not because it doesn't exist, but because you're protected from most of it. The planet itself provides layers of shielding that work silently in the background. The atmosphere absorbs a large portion of incoming radiation, especially the more harmful types. The magnetic field deflects charged particles, guiding them away before they reach the surface. Together, these systems create a kind of invisible barrier. You live inside it every day, and because it's always there, it becomes easy to forget that beyond it, conditions are very different. The Moon sits outside most of that protection. It has no global magnetic field like Earth's, and as we've already explored, it has no atmosphere, which means that anything travelling through space, particularly high-energy particles, can reach the surface directly. And those particles are not rare, they come from multiple sources. The most immediate is the Sun. It constantly emits a stream of charged particles known as the solar wind. Under normal conditions, this flow is relatively steady, but occasionally the Sun releases much larger bursts, solar flares, and coronal mass ejections, which send intense waves of radiation outward. On Earth, these events are mostly deflected or absorbed. On the Moon, they arrive unfiltered. If you were standing on the lunar surface during one of these events without adequate shielding, exposure could increase rapidly. And again, this is not something you would feel happening. There's no sensation that warns you, no immediate signal that something is wrong. The risk builds silently. Beyond the Sun, there's another source that is even more persistent: cosmic radiation. These are high-energy particles originating from outside our solar system, sometimes from distant supernovae or other energetic events in the galaxy. They travel at incredible speeds, crossing vast distances, and they don't stop easily. When they encounter matter, they can pass through it, interacting at a microscopic level. On Earth, many of these particles are slowed or redirected before they reach you. On the Moon, they are part of the environment, constant, steady, and unavoidable without protection. Now, radiation might sound abstract, but its effects are very real. At a basic level, it interacts with cells. High-energy particles can damage DNA, disrupt cellular processes, and over time increase the risk of long-term health issues. The important part is that this damage doesn't need to be dramatic to matter. It accumulates. A little exposure over time becomes significant, and because you don't feel it as it happens, it's easy to underestimate. There's no immediate discomfort to remind you to be cautious. No pain that tells you to move away. It's something that requires awareness, planning, and protection, even though it doesn't announce itself. For astronauts, this has always been a concern. Even in low Earth orbit, where some of Earth's magnetic protection still exists, radiation exposure is higher than on the surface. On the Moon, the exposure would be greater, which means that any long-term presence there has to account for it carefully. Habitats would need shielding, spacesuits would need to provide some level of protection. Activities would need to be planned with timing in mind, avoiding periods of increased solar activity. It becomes part of the environment in the same way temperature or dust does, something you have to consider continuously. There's also an interesting interaction between radiation and the Moon's surface itself. When high-energy particles strike the regolith, they can generate secondary radiation. New particles produce from the interaction, which then move outward again. So even the ground beneath your feet contributes to the overall exposure. It's not just what's coming from above. It's what happens when it reaches the surface, and again, none of this is visible. You can look around and see nothing unusual. The sky remains dark. The landscape remains unchanged. There are no visual cues to indicate that anything is happening at all, which makes it one of the more subtle challenges of being on the Moon, because it requires you to trust what you cannot perceive directly, to rely on measurements, on planning, on systems designed to keep you within safe limits. And if those systems fail, even temporarily, the environment doesn't give you a second chance to notice and adjust. There's also the matter of duration. Short exposure might not lead to immediate problems, but longer stays increase the risk. And as we begin to think about returning to the Moon, not just visiting for a few days, but staying for weeks, months, or longer, that cumulative effect becomes more important. It's not just about surviving the environment, it's about living in it safely over time, which means understanding not only what is happening, but how it builds. Radiation doesn't rush. It doesn't need to. It simply continues, steady, consistent, interacting with everything in its path. And that consistency is what makes it significant, because it doesn't stop. There's no moment when the Moon becomes safe from it. It is always present. From Earth, this is completely hidden. You see the Moon as a bright object against a dark sky, calm and unchanged. You don't see the streams of particles moving through space. You don't see the interactions happening at the surface. You don't see the gradual effects over time. And because you don't see them, it's easy to assume they're not there. But they are. Part of the environment, just as much as the lack of air, the temperature extremes, the dust and the low gravity. Each one contributing in its own way to a place that is far less gentle than it appears from a distance. And what makes radiation particularly interesting is how it connects the Moon to the larger environment of space. Because it's not something unique to the Moon. It's something the Moon is fully exposed to, without the layers of protection that make Earth feel stable, predictable and safe. Which means that being on the Moon is, in a way, being closer to space itself, experiencing more directly what exists beyond the boundaries we usually live within. By now, the Moon might feel less like a quiet object in the sky, and more like a place defined by things you don't immediately notice, not loud dangers, not sudden threats, but steady conditions that are always present. And there's one more of those conditions that comes not from the moon itself, but from everything moving through space around it. Tiny objects, so small that you wouldn't notice them individually, so common that they are always there. Micrometeorites. On Earth, objects from space enter the atmosphere all the time. Most of them are incredibly small, no bigger than grains of sand. As they pass through the air, friction builds, heat increases, and they burn up before reaching the ground. That's what creates shooting stars, brief streaks of light that appear and disappear in seconds. They're harmless because the atmosphere handles them for you. It slows them down, it breaks them apart, it turns them into something you can watch instead of something you have to worry about. The moon has no such protection. There is no atmosphere to slow incoming objects, no layer of air to burn them up, so even the smallest particles reach the surface, and they don't arrive gently. They travel at speeds that can exceed tens of kilometers per second. That's faster than anything you experience in daily life. At those speeds, even something extremely small carries a surprising amount of energy. A particle the size of a grain of sand becomes something more like a tiny projectile, and because these particles are so numerous, the moon is constantly being struck by them. Not occasionally, continuously. Every moment, somewhere on the lunar surface, a micrometeorite is arriving. Most of the time, the impacts are too small to notice at a distance. They don't create large craters. They don't produce visible changes that you could easily detect from Earth. But over time, they shape the entire surface. They grind down rocks. They create the fine dust layer that covers everything. They leave behind a record of constant interaction between the moon and its surroundings. And if you're there, standing on that surface, those same impacts are happening around you. Again, this isn't something you would hear. There's no sound to carry the impact, no warning, no indication that something is incoming. The particle arrives, strikes, and that's it. If it hits the ground nearby, it becomes part of the ongoing process that shapes the surface. If it hits something else, equipment, a structure, a suit, then it becomes a direct concern. Now it's important to keep this in perspective. Not every micrometeorite is large enough to cause serious damage. Many are extremely small, but size matters less when speed is involved. Because kinetic energy increases rapidly with velocity, a tiny particle moving at extreme speed can still create a noticeable impact. Over time, repeated exposure leads to wear. Surfaces experience tiny pitting. Materials weaken gradually. Protective layers must account for this constant low-level bombardment. This is why spacecraft and equipment designed for use in space often include shielding, not just for large impacts which are rare, but for these countless small ones that occur regularly. Layers are designed to absorb or disperse the energy, reducing the likelihood of penetration. But even with protection, the risk is never completely removed. It's managed, reduced, accounted for, but still present. And because it's continuous, it becomes part of the environment in the same way dust and radiation are. Something that doesn't stop, something that doesn't pause, something that doesn't give you a moment where it simply isn't happening. There's also an interesting effect on the surface itself. Over long periods, micrometeorite impacts contribute to the moon's appearance. The lack of atmosphere means that once a mark is made, it stays. There's no wind to erode it, no water to smooth it out. Every impact, no matter how small, becomes part of the landscape, accumulating over billions of years, which is why the moon is covered in craters, from massive basins to tiny pits, each one a record of something arriving from space. And that process hasn't stopped. It continues today, at the same quiet, steady pace. Now, imagine being there, knowing that this is happening constantly. You don't see the particles, you don't hear them, but you know they are arriving. That knowledge changes how you think about exposure. It's not about avoiding a single event. It's about existing in an environment where events are happening all the time. And while most of them are small, the possibility of encountering something slightly larger is always there. Not common, but not impossible. Which is why structures on the moon would need to be designed with this in mind. habitats would require shielding, not just for radiation, but for physical impact as well. Layers that can absorb energy, prevent penetration, and maintain integrity over long periods. Even something as simple as a window becomes more complex. Transparent materials must be strong enough to withstand repeated impacts without degrading too quickly. Surfaces must be maintained, inspected, repaired if necessary. Because unlike on Earth, there's no natural process that helps remove damage. Everything accumulates. There's also a subtle psychological aspect to this. Living in a place where the environment is constantly interacting with you, even in small ways, creates a different kind of awareness. You're not just moving through a static landscape, you're in a dynamic system, one that is active, even if that activity is invisible. That can feel different, not alarming but present. A reminder that the moon is not isolated from the rest of space. It is fully part of it, exposed to everything moving through it, and you, standing there, are part of that exposure as well. It's interesting how this connects back to something we mentioned earlier, the idea that space feels empty. From a distance it looks like nothing, a vast dark expanse with very little happening. But in reality it's full of motion, particles, radiation, objects of all sizes moving at high speeds. The difference is that most of that activity doesn't produce light or sound in a way we can easily perceive, so it feels empty even when it isn't. The moon sits in that environment without protection, which means it experiences all of it directly, and that direct exposure is what defines so many of its characteristics. The dust, the craters, the constant subtle changes to its surface, all shaped by things arriving from beyond. From Earth, none of this is obvious. You see the larger features, the dark patches, the bright highlands, the familiar patterns that give the moon its appearance. But you don't see the ongoing process, the continuous interaction, the steady arrival of tiny objects that, over time, make a difference. And just like with radiation, just like with dust, this is something that doesn't announce itself. It doesn't draw attention, it simply continues. Which is why understanding the moon means looking beyond what is visible, thinking about what is happening quietly, consistently in the background. Because those processes, the ones that don't stand out immediately, are often the ones that define the experience most clearly. And when you begin to put them together, the lack of air, the temperature extremes, the dust, the radiation, and now this constant bombardment, the moon starts to feel less like a passive object and more like a place shaped by ongoing activity. If you've ever looked at the moon on a clear night, really looked at it, you might have noticed that it isn't smooth at all. Even without a telescope, there are patterns, dark patches, lighter regions, subtle textures that give it character, and with even a small amount of magnification, those details become clearer. Circular shapes, depressions, marks that seem scattered across the surface in no particular order. Those are craters, and they are everywhere. The moon is covered in them, from massive basins hundreds of kilometers wide to tiny pits so small they blend into the dust. There are so many that, in some regions, they overlap, one forming on top of another, layers of impact stacked across time. At first, they can look almost decorative, part of the moon's natural appearance. But each one represents an event, an impact, something arriving from space at high speed and releasing its energy in a single moment. And when you begin to think of the surface that way, not as a static landscape, but as a record of events, the moon starts to tell a different story, one that is far more active than it appears from a distance. On Earth, we don't see many craters like this. Not because impacts don't happen, but because our planet is constantly changing. Wind, water, tectonic activity, vegetation, all of these processes reshape the surface over time. Craters are worn down, filled in, covered up, or erased completely. The Earth forgets. The moon does not. There is no atmosphere to erode features, no water to smooth edges, no tectonic movement to recycle the surface. So when something strikes the moon, the mark it leaves behind stays. For a very long time, millions, sometimes billions of years. That's why the moon's surface looks the way it does. It's not just a place, it's a record, a history written in impacts, and that history is not gentle. In the early days of the solar system, about 4 billion years ago, the environment was far more chaotic than it is now. Leftover material from the formation of planets, fragments of rock and metal, moved through space in large numbers. Many of those objects collided with the moon. This period is sometimes referred to as the late heavy bombardment. During that time, impacts were frequent and often large. Massive objects struck the surface, releasing enormous amounts of energy, melting rock, reshaping entire regions. Some of the largest craters you see today were formed during this era. Basins so wide that they span hundreds of kilometers. One of the most noticeable is the Imbrium Basin, a large dark area visible even from Earth. It was created by a massive impact that not only formed a deep depression, but also caused molten material to spread out and solidify, creating the darker plains we now call Maria. These darker regions are smoother than the surrounding highlands, which is why they stand out, but even they are marked by smaller craters. Because the impacts didn't stop, they became less frequent over time, but they never completely ceased. Even now, the moon continues to be struck by objects from space, small ones mostly, micrometeorites as we've discussed. But occasionally larger impacts still occur, and because there is nothing to erase them, each new crater adds to the record, layer upon layer, overlapping histories. Some craters are so old that their edges have softened slightly, not by erosion, but by the accumulation of smaller impacts over time. Others are sharp and well-defined, indicating more recent formation. If you look closely, you can see these differences, a kind of timeline etched into the surface. Older features partially covered by newer ones, patterns that show which events came first and which followed. It's a bit like reading a story where each page is written on top of the previous one, but the earlier words are still faintly visible beneath. Now imagine standing on that surface, not looking at it from a distance, but being surrounded by it. Craters wouldn't just be patterns, they would be part of the terrain. Some shallow, some deep. Some small enough to step across, others large enough that you wouldn't see the far side without moving. The ground would rise and fall in subtle ways, shaped by countless impacts over time, and each of those features would represent a moment when something struck the moon with enough force to change it. That awareness changes how you think about the place, because it's not just that the moon was once active, it's that the process that created those features is still part of its environment. Impacts still happen. The difference is scale and frequency. The large dramatic events are rare now, but the smaller ones continue, and they remind you that the moon is not isolated from space. It is exposed to it, completely. There's also something else that craters reveal. The energy involved in these impacts. Even a relatively small object, when moving at high speed, carries significant energy. When it strikes the surface, that energy is released instantly. Rock can melt. Material can be ejected outward, forming rays that extend from the crater. Debris can travel long distances before settling. All of this happens in a moment. A single event leaving a permanent mark. Now scale that up. Consider larger impacts, the kind that create basins visible from Earth. The energy involved in those events is enormous, far beyond anything we experience in everyday life, and yet the moon bears the evidence of many such events, which means that, at some point in its history, it experienced conditions that were far more intense than anything we see today. A period where impacts were not rare, but common, where the surface was constantly being reshaped, where stability, in the sense we understand it, didn't exist. That past is still visible. Every time you look at the moon, you are seeing the result of those events. Not as something abstract, but as physical features that remain unchanged. And because they remained, they give us insight into what the moon has been through. A kind of memory, one that doesn't fade. From Earth, This can feel distant, almost historical in a detached way, something that happened long ago, no longer relevant. But when you consider that the same processes, smaller now but still active, continue to affect the moon, it becomes more immediate, more connected to the present. Because the difference between past and present on the moon is not as clear as it is on Earth. The environment hasn't changed in a way that removes those processes, it still allows them. Which means that being on the moon is not just being in a place shaped by past events, it's being in a place where similar events, on a smaller scale, still occur. And while the chances of encountering a large impact are low, the environment itself is defined by the possibility, by the fact that space is not empty and the moon has no protection from what moves through it. There's also a kind of quiet contrast here. The moon looks calm, unchanging, a steady presence in the sky. But that appearance is the result of a lack of change in one sense: erosion, weathering, surface renewal, combined with a long history of change in another, impacts. It's a place where the past remains visible, because nothing has come along to remove it, which creates the impression of stillness, even though that stillness is built on a history of constant interaction. And when you begin to see it that way, the moon becomes something more complex. Not just a quiet object, but a surface that has been shaped by forces acting over immense periods of time, forces that are still present, even if they are less dramatic now. It's a reminder that calm appearances can be misleading, that what looks stable from a distance may be the result of processes that are anything but gentle, and that understanding a place often means looking beyond what it looks like now and considering how it came to be. Because once you do that, once you start to connect the surface features to the events that created them, the moon story becomes clearer. Not a story of stillness, but of interaction, of constant contact with the space around it. While we've been focusing on what the moon is like as a place, there's another side to this story, what the moon does. Not on its own surface, but here, on Earth, and it begins with something so familiar that it almost disappears into the background. The tides. If you've ever been near the ocean, you've seen them. The water slowly rising, then falling, following a rhythm that repeats day after day. It feels natural, expected, almost like breathing on a planetary scale. But that motion is not random. It's driven largely by the moon, through gravity. Now, gravity is something we experience constantly, but we rarely think about how it varies across distances. The moon's gravity pulls on Earth, not strongly enough to move the entire planet in a noticeable way, but enough to affect things that can respond more easily, like water. The oceans are not fixed. They can shift, flow, and adjust. So when the moon's gravity pulls on Earth, it creates a slight bulge in the water on the side facing the moon. At the same time, there's another bulge on the opposite side, caused by the way the Earth and moon move together. The result is two areas of higher water levels. As the Earth rotates, different parts of the planet pass through these bulges, and that's what we experience as tides. A slow rise and fall of the ocean, twice each day in most places. It doesn't feel like a force. It feels like a pattern, but that pattern is the result of a continuous gravitational interaction between the Earth and the moon, an interaction that never stops. Every moment the moon is pulling, and the Earth is responding. Now, tides might not seem dangerous. They're predictable, measured, something we've adapted to over time. But their influence goes beyond just the visible movement of water. They shape coastlines. They affect ecosystems. They influence navigation, weather patterns, and even the distribution of nutrients in the oceans. Over long periods, tides contribute to erosion, gradually reshaping land. They also create environments where life is adapted to constant change. Intertidal zones, where organisms live between high and low tide, depend entirely on this rhythm. Remove the moon, and those environments would change completely. But there's another aspect to this interaction that is less visible: the transfer of energy. As the moon pulls on Earth's oceans, the movement of water creates friction. That friction slows the Earth's rotation very slightly, not enough to notice in a day or even a lifetime, but measurable over long periods. Billions of years ago, a day on Earth was shorter. The planet rotated more quickly, but over time, the gravitational interaction with the moon has gradually slowed that rotation, lengthening our days. At the same time, the moon itself is moving away from Earth very slowly, about 3.8 centimeters per year. It's a small distance, but over millions of years it adds up. This is part of the same system. Energy being transferred, motion being adjusted, both bodies influencing each other. So the moon is not just something that orbits Earth, it is part of a dynamic relationship, one that affects the entire planet. And while that relationship feels stable now, it's important to remember that it is still an active process. It hasn't stopped. It continues every day. Now imagine for a moment that this interaction were different. If the moon were closer, its gravitational pull would be stronger. Tides would be more extreme. Higher highs, lower lows. Coastlines would experience more dramatic changes. Flooding in some areas would become more frequent. The balance we're used to would shift. If the moon were farther away, the opposite would happen. Tides would become weaker, less movement, less mixing in the oceans. That might sound calmer, but it would also affect ecosystems that rely on that motion. Life along coastlines would adapt differently, or struggle to adapt at all. So the current state, the one we're familiar with, is not just a coincidence. It's the result of a specific distance, a specific gravitational relationship that has developed over time. And that relationship has played a role in shaping the Earth as we know it. There's also an effect on the planet's stability. The moon helps stabilize Earth's axial tilt, the angle at which the planet is tilted relative to its orbit around the sun. That tilt is what creates seasons. Without the moon's stabilizing influence, that tilt could vary more dramatically over time, leading to more extreme shifts in climate, more unpredictable changes in seasons. So even though the moon feels distant, its presence contributes to the conditions that make Earth relatively stable, which means that the moon's influence is not just about movement, it's about balance, a quiet, ongoing contribution to how the planet behaves. And again, none of this is something you feel directly. You don't wake up and notice the moon pulling on the ocean. You don't sense the slowing of Earth's rotation. You don't observe the gradual movement of the moon away from the planet. These are processes that happen over long timescales, subtle, continuous, and because they are subtle, they become easy to ignore. But they are always there, shaping the environment in ways that are not immediately obvious. Which brings us back to the idea of the moon being more than it appears. From Earth, it looks calm, passive, a light in the sky. But in reality, it is part of a system that influences the entire planet. Not through sudden events, but through steady interaction. And while that interaction is not dangerous in the sense we usually think of, it is powerful, because it operates on a scale that is difficult to notice in the moment, yet significant over time. It's also a reminder that the moon is not separate from Earth. The two are connected, through gravity, through motion, through shared history. And that connection means that changes to one can affect the other. Which leads to an interesting question. What if that connection were suddenly broken? What if the moon, this constant presence, simply wasn't there anymore? How different would things be? Imagine stepping outside tonight, looking up at the sky as you normally would, and noticing that something is missing. Not hidden behind clouds, not dim, not partially visible, just gone. No moon at all. At first, it might not feel dramatic. The night sky would still be there. Stars would still fill the darkness, perhaps even more clearly than before, without the moon's brightness softening them. In some ways, it might even look more vivid. But that calm impression wouldn't last very long, because the moon is not just something you see. It's something that quietly supports the way Earth behaves, and removing it would begin a chain of changes that unfold in layers, some immediate, some gradual, but all connected. The first thing you would likely notice beyond the absence itself is the darkness. Moonlight doesn't seem very strong when you compare it to sunlight, but at night it makes a difference. A full moon can illuminate landscapes, cast shadows, and provide enough light to move around without artificial sources. Without it, nights become darker, not just slightly darker, noticeably so. In rural areas, far from city lights, the difference would be especially clear. Paths that were once faintly visible would disappear into shadow. The contrast between objects would soften, making the environment feel less defined. It wouldn't be dangerous on its own, but it would change how night feels, more distant, more empty. Then, over the next hours and days, something less obvious would begin to shift. The tides. Without the moon's gravitational pull, the oceans would no longer experience the same pattern of rising and falling. There would still be some tidal movement, caused by the sun, but it would be much weaker. About a third of what we experience now. That means the familiar rhythm of high and low tides would fade. Coastal regions would change, not instantly, but steadily. Areas that rely on tidal flow would begin to behave differently. Water would move less. Nutrients that are normally stirred and distributed by tides would settle differently. Ecosystems that depend on that constant movement, especially in intertidal zones, would be affected. Some species might adapt, others might not. Over time, coastlines themselves would begin to change. Not dramatically at first, but in subtle ways. Erosion patterns would shift. Sediment would accumulate differently. The steady reshaping of land by the ocean would follow a new pattern. And because these changes happen gradually, they might not be immediately noticeable, but they would be real. Then there's something even less visible, but just as important: the length of the day. Right now, the moon's gravitational interaction with Earth is slowly slowing down the planet's rotation. It's a very gradual process, but it's happening continuously. Remove the moon, and that braking effect disappears. The Earth would stop slowing down at its current rate. The length of the day would stabilize at whatever it happens to be at that moment. That might not seem significant, but it's part of a larger system that has been shaping Earth for billions of years. A system that would suddenly be interrupted. There's also the question of Earth's tilt. The planet is tilted at about 23.5 degrees relative to its orbit around the Sun. That tilt is what gives us seasons: spring, summer, autumn, winter. Without the moon, that tilt would become less stable over very long periods of time. It wouldn't change overnight. But over thousands, millions of years, it could begin to vary more dramatically. That means the angle of sunlight reaching different parts of Earth could shift in ways that are less predictable. Seasons could become more extreme or less consistent. Climate patterns that have remained relatively stable could begin to drift. Again, not immediately, but inevitably. Then there's the psychological aspect. The moon has always been part of human experience. It appears in stories, in calendars, in the way we mark time. Months are based on its cycle. Cultural traditions, events, and even language are tied to its phases. Remove it, and that connection disappears. There would be no full moon, no crescent, no gradual waxing and waning. The sky would lose a familiar rhythm. Something that has been constant throughout human history would no longer be there. And that absence would be felt, even if it's difficult to describe exactly how. But perhaps the most interesting part of this thought experiment is not what changes immediately, but what it reveals about how much we rely on something we rarely think about. The moon feels distant, optional, like something that could be removed without consequence. But that's only because its influence is steady, predictable. It doesn't call attention to itself. It doesn't create sudden disruptions that force you to notice it. Instead, it operates quietly, maintaining patterns, supporting systems, providing a kind of background stability. And because it does all of this without interruption, it becomes easy to assume that it's not essential, until you imagine it gone. Then you start to see the connections, the way tides respond to its pull, the way Earth's rotation is influenced over time, the way the planet's tilt remains relatively stable, the way ecosystems, coastlines, and even human culture have adapted to its presence. All of these things are linked, not in a dramatic, obvious way, but in a continuous, subtle way. Remove the moon, and those links begin to loosen. Some break quickly, others take time, but the system changes, and that's what makes the moon interesting in this context. It's not just about what happens on its surface, it's about how it fits into a larger system, a system that includes Earth. Because the moon is not just orbiting us, it's interacting with us, constantly, and that interaction has been shaping both bodies for a very long time, which leads to another question. If the moon can influence Earth in these quiet but powerful ways, what about the reverse? What about the stability of the moon's own orbit? Could it ever change in a way that brings it closer, or alters its path? There's a certain comfort in looking up and seeing the moon exactly where you expect it to be. Not drifting unpredictably, not changing course, just following the same path it always has, night after night, year after year. That consistency creates a quiet assumption that the moon's position is permanent, that its orbit is fixed, that nothing about its motion will ever change in a meaningful way. But when you begin to look more closely at how objects move in space, that assumption starts to soften. Because orbits are not static. They are the result of motion, gravity, and balance. And balance, even when it appears stable, is always the result of forces interacting continuously. The moon is not simply hanging above Earth. It is falling, constantly, just not in the way we usually think about falling. If you drop something on Earth, it moves straight down. Gravity pulls it toward the ground, and without anything to counter that motion, it continues until it reaches the surface. The moon is also being pulled toward Earth by gravity. That part is the same. The difference is that the moon is also moving sideways, very fast. Fast enough that as it falls toward Earth, it keeps missing it. That sideways motion, combined with the downward pull of gravity, creates a curved path, an orbit. So in a very real sense, the moon is always falling toward Earth. It just never reaches it. Now, that might sound stable, and in many ways it is, but it's important to understand that this stability is not because nothing is happening. It's because everything is happening in a very precise balance. Gravity pulls inward, motion carries outward, and the result is a path that repeats. But that path is not fixed forever. In fact, we know that the moon's orbit is changing, very slowly, very steadily. Every year the moon moves about 3.8 centimeters farther away from Earth. It's a small distance, barely noticeable in the short term. But it's measurable, and over long periods, it becomes significant. This outward movement is part of the same interaction we discussed earlier with tides. As the moon pulls on Earth's oceans, the movement of water creates friction. That friction transfers energy. Some of that energy is passed to the moon, giving it a slight boost in its orbit, and that boost causes it to move farther away. So rather than falling toward Earth, the moon is actually drifting away from it, at least for now. That raises an interesting question. If the moon is moving away, could that ever change? Could something alter its motion in a way that brings it closer instead? Could the balance shift? To answer that, it helps to think about what would be required for the moon to fall toward Earth in the way we might imagine. For that to happen, the moon would need to lose some of its sideways motion. Its orbital speed would have to decrease, because it's that speed that keeps it from spiraling inward. If that speed were reduced even slightly, the balance would change. Gravity would begin to dominate more strongly. The moon's path would curve inward, and over time it could move closer. But in the current system, there is no natural process that significantly slows the moon down in that way. The interactions we observe actually push it outward, not inward. So under normal conditions, the idea of the moon suddenly falling toward Earth is not something we expect. However, Space is not a perfectly isolated system. There are other forces at work, other objects, other influences. The Sun, for example, plays a major role in the Earth-Moon system. Its gravity affects both bodies. In fact, the Earth and Moon together orbit the Sun, and the Sun's gravitational pull is stronger than Earth's pull on the Moon. But because the Moon is much closer to Earth, it remains bound in orbit around it. The balance between these forces is stable, but it is still a balance, and balances can, in theory, be disrupted. For the Moon's orbit to change significantly, something would need to introduce a new force, a large one, a passing object with enough mass to alter the system, or a change in the distribution of mass within the Earth-Moon system itself. These scenarios are extremely unlikely. They would require conditions that are rare on cosmic timescales, but they are not impossible in the absolute sense. Space is dynamic, objects move, systems evolve. Over very long periods, interactions can accumulate. But even without dramatic events, the Moon's orbit is not perfectly circular. It is slightly elliptical, which means that its distance from Earth varies over time. At its closest point, called perigee, it is about 363,000 kilometers away. At its farthest, called apogee, it is about 405,000 kilometers away. This variation is part of its normal motion, and it contributes to subtle differences in how we perceive the Moon from Earth. Sometimes it appears slightly larger, sometimes slightly smaller, but these changes are part of a stable pattern, a repeating cycle. So while the Moon's orbit is not perfectly fixed, it is predictable, reliable, at least on the timescales we experience. Now, there is another way to think about instability, not as a sudden change, but as something that could occur over extremely long periods, hundreds of millions or billions of years. As the Moon continues to move away from Earth, the gravitational interaction between the two bodies will weaken. Tidal effects will become smaller. The system will evolve. Eventually, the Earth's rotation and the Moon's orbit could reach a kind of equilibrium, where the same side of Earth always faces the Moon, just as the same side of the Moon currently faces Earth. At that point, the transfer of energy would stop, and the Moon would settle into a more stable, distant orbit. This is a natural progression of the system, not a collapse, not a fall, but a gradual adjustment. A movement toward a different kind of balance. So in that sense, the Moon is not in danger of falling toward Earth. It is, if anything, moving away. But the idea of it falling is still useful, because it highlights something important about how orbits work. They are not static positions, they are dynamic states, maintained by motion and force, and while they can be stable for very long periods, they are not permanent in the absolute sense. They depend on conditions remaining consistent, on forces continuing to interact in the same way, which brings us back to perception. From Earth, the Moon feels fixed, reliable, always where it should be. But that feeling comes from observing it over a relatively short period of time, a human lifetime, a few generations. Compared to the age of the Earth-Moon system, that's almost nothing. On longer timescales, change is always present. Even if it's slow, even if it's subtle, and understanding that doesn't make the Moon feel unstable in a practical sense. You don't need to worry about it falling tomorrow or next year, or even millions of years from now. But it does change how you think about it. It shifts the perspective from something permanent to something evolving. A system in motion, maintained by balance but not immune to change. And that idea connects to something else we've been exploring throughout this journey. The difference between how things appear and how they actually behave. The Moon appears calm, stable, unchanging. But beneath that appearance is a complex interaction of forces, gravity, motion, energy transfer, all working together to create the path we observe. And while that path is stable now, it exists because of those forces, not in spite of them. Which means that the Moon is not just sitting in the sky, it is moving, constantly, following a path defined by balance. And that balance, while reliable, is not the same as being fixed forever. It's a reminder that even the most familiar things, the ones that feel permanent, are part of systems that are always in motion, even if that motion is too slow to notice, even if it takes a different perspective to see it clearly. And as you begin to think about the moon in that way, not just as something you observe, but as something moving, interacting, evolving, it opens up another layer of understanding. Look up at the moon often enough, and you'll start to notice something that feels almost like a quiet habit. It always seems to show you the same face, the same patterns, the same dark patches and lighter regions arranged in a way that becomes familiar over time. You don't have to study it closely to recognize it. Even a brief glance is enough. And that familiarity leads to an assumption that what you see is the moon, not part of it, not a portion, but the whole thing. Yet that isn't quite true. What you're looking at every time you see the moon from Earth is just one side, the same side. Always. This is not a coincidence. It's the result of something called tidal locking, a process that has taken place over a very long time. The moon rotates on its axis at the same rate that it orbits Earth. So as it moves around our planet, it turns just enough to keep the same hemisphere facing us. It's a kind of synchronization, a balance that has settled into place, which means there is another side of the moon that we never see directly from Earth. And that's where the idea of the dark side comes from. It sounds mysterious, almost like a hidden region that never receives light, a place permanently in shadow, but that's not accurate. The far side of the moon, the side we don't see, receives just as much sunlight as the near side. It experiences the same long days and long nights, the same cycles of light and darkness. There is no permanent shadow across half of the moon. The term dark side is more about what is unseen than what is unlit. It's the side hidden from our view, and because it's hidden, it invites a certain kind of imagination. For a long time, before spacecraft allowed us to observe it directly, that far side was unknown. People speculated about what might be there, whether it would look the same as the side we see, or something entirely different. And when we finally did get a clear look at it, the answer was interesting. It is different. Not dramatically in shape or structure, but in detail. The far side has far fewer of the large dark planes, the Maria, that are visible on the near side. Instead, it is more heavily covered in craters, more rugged, more uneven. The surface tells a slightly different story, and that difference is thought to be related to the moon's history, its internal structure, and how it cooled over time. But what matters more in this context is not just what the far side looks like, it's what it represents, because it highlights a simple but important idea. We're used to seeing only part of the moon, and over time we've come to think of that part as the whole. It's a kind of observational bias. We build our understanding based on what is visible, and we tend to forget that there is more beyond that. Now, this doesn't make the far side dangerous in itself, but it does connect to the broader theme we've been exploring, the difference between appearance and reality. The moon looks calm, it looks consistent, it shows us the same face night after night. But that consistency is the result of a specific alignment, a specific relationship between rotation and orbit, one that keeps part of the moon hidden, and that hidden portion reminds us that what we see is not always complete. There's also something else about this alignment that's worth considering. Because the moon is tidally locked, one side always faces Earth. That means the far side always faces away. And that has practical implications. Communication, for example. If you were on the far side of the moon, you would not have a direct line of sight to Earth. Signals would not travel straight between you and the planet. You would need a relay system, something in orbit or positioned in a way that can carry the signal around the moon. Without that, you would be cut off, not because of distance, but because of orientation. The moon itself would block the connection. This creates a kind of natural isolation. The far side is not just unseen, it is, in a direct sense, separated, and that separation is unique. On Earth, there are always ways to communicate across the planet. Signals can travel through the atmosphere, bounce off satellites, move through networks. But on the Moon, the geometry of its orbit creates a region where direct communication with Earth is not possible unless you plan for it, which adds another layer to the experience of being there. It's not just about the environment, it's about position, where you are relative to Earth, and how that affects your ability to connect. There's also an interesting visual aspect to this. From Earth, we see the same patterns on the Moon's surface. Those patterns become familiar. They form shapes that people recognize, sometimes even imagining faces or figures within them. It's a kind of pattern recognition, the human mind looking for meaning in what it sees. But those patterns exist only on the side we can observe. The far side has its own patterns, its own arrangement of features, but they are not part of our everyday experience, which means that our mental image of the Moon is incomplete, not wrong, just partial. And that partial view can influence how we think about it. It can make the Moon feel simpler than it is, more uniform, more predictable. Because we're always seeing the same aspect, but in reality the Moon is a three-dimensional object with variation across its entire surface, differences in terrain, in composition, in history, and the far side is a reminder of that complexity. Now, there's also a subtle connection between tidal locking and the stability we discussed earlier. The reason the Moon became tidally locked is because of gravitational interactions with Earth. Over time, those interactions slowed the Moon's rotation until it matched its orbital period. That process took millions of years, and it resulted in the stable configuration we see today. But again, this stability is the result of forces acting over time, not something that was always there, which means that even the way the Moon presents itself to us is the outcome of a long process, one that has shaped not just its motion, but our experience of it. From Earth, the Moon feels consistent, reliable, always showing the same face, but that consistency is part of a larger system, one that includes hidden aspects, unseen regions, and interactions that are not immediately obvious. And when you begin to think about it that way, the Moon becomes a little less familiar, not because it changes in front of you, but because you start to realize how much of it you don't see, how much of it exists beyond your direct observation, and that idea extends beyond just the surface. Because there are aspects of the Moon that are not visible at all, not because they are hidden behind its rotation, but because they don't produce anything you can detect with your senses, things that require instruments to measure, phenomena that occur quietly without light or sound. And those aspects, just like the far side, are easy to overlook until you start paying attention to what they reveal. Step outside on a clear night when a lunar eclipse is taking place, and something feels different almost immediately. The Moon is still there, it hasn't moved, it hasn't changed its position in the sky, and yet it doesn't look the same. Its usual pale brightness fades, slowly at first, then more noticeably. The familiar glow that reflects sunlight so gently begins to dim, as if someone is quietly turning down a light you didn't realize could change. Then, gradually, it takes on a different color, a deep, muted red, not bright, not glowing in the way you might expect, but present, steady, unusual enough that it captures your attention in a way the full moon normally doesn't, and in that moment, the Moon no longer feels quite as calm as it usually does. Not because anything dangerous is happening directly, but because the change itself is unfamiliar. It breaks the pattern. And whenever something breaks a pattern we've come to rely on, it introduces a subtle sense of unease. Now, what's actually happening during a lunar eclipse is something very precise. The Earth moves directly between the Sun and the Moon. Its shadow stretches out into space, and the Moon passes through it. At first, the outer part of that shadow, the penumbra, causes only a slight dimming. It's easy to miss if you're not looking closely. But as the Moon moves deeper into the Earth's shadow, into the umbra, the effect becomes much more noticeable. Direct sunlight no longer reaches the surface, and yet, the Moon doesn't disappear completely. Instead, it glows faintly red. That colour comes from Earth's atmosphere. Sunlight passing through the edges of the atmosphere is filtered, with shorter wavelengths scattered away, and longer, red wavelengths bending into the shadow. So even though the moon is in darkness, it is still being illuminated indirectly by light that has travelled through the entire edge of Earth's atmosphere. It's a quiet reminder that even in shadow, there are connections between bodies in space, light bending, paths changing, interactions that are not immediately obvious. But while the physics behind it is well understood, the experience of seeing it still feels different. Because for most of the time the moon is predictable. It reflects sunlight consistently, it follows its phases, it behaves in ways that are easy to anticipate. A lunar eclipse interrupts that. It introduces a change that is not part of the regular nightly rhythm. And that change makes the moon feel less stable, even if only for a short time. Throughout history, this effect has been noticed. Long before the mechanics of eclipses were understood, people observed the moon darkening, changing colour, and then returning to normal. Without an explanation, that kind of event can feel significant, unusual enough to be interpreted as a sign of something important, something out of the ordinary. Even today, with all the scientific understanding we have, the experience still carries a certain weight, because it's not something you see often. It doesn't happen every month. It appears occasionally, and when it does, it changes the way the moon looks in a very visible way. Now, from a physical standpoint, a lunar eclipse doesn't make the moon more dangerous. It doesn't change its surface conditions. It doesn't alter its environment. But it does highlight something about shadows and light that becomes much more relevant when you think about being on the moon itself. Because shadows on the moon are not like shadows on Earth. On Earth, shadows are softened by the atmosphere. Light scatters, edges blur. Even in shade, there is still some ambient light. You can see into shadows. You can adjust. On the moon, shadows are sharp, defined. Because there is no atmosphere to scatter light, the transition from light to dark is immediate. One step, and you move from full brightness into near total darkness. There is no gradual fade, no adjustment period, and within those shadows, conditions change quickly. As we discussed earlier, temperature drops sharply in the absence of sunlight. So a shadow is not just a visual change, it's an environmental one, a place where heat disappears, where surfaces cool rapidly, where the conditions become more extreme. Now imagine that on a larger scale. During a lunar eclipse, the entire visible surface of the moon is effectively in shadow. Not the same kind of shadow as a small crater or a rock, but a global version of it. The sunlight that normally heats the surface is blocked. The temperature begins to drop. And while this change is gradual over the course of the eclipse, it still reflects the same principle. Without sunlight, without an atmosphere, the moon loses heat. Directly. There is no system to retain it. And that's what makes shadows on the moon more than just areas of reduced light. They're regions of different conditions. Places where the environment shifts in ways that matter. There's also an interesting aspect to how we perceive this from Earth. When the moon turns red during an eclipse, it can feel almost symbolic. A shift from something familiar to something slightly unsettling. Not because it's dangerous, but because it's different. It reminds you that the moon is not producing its own light, that its appearance depends entirely on its position relative to the Earth and the Sun. Change that position, and the appearance changes, which means that what you see is not fixed, it's dependent, contextual. And that idea connects back to something we've been exploring throughout this journey. The moon's calm appearance is not a property of the moon alone. It's the result of how light reaches it, how we observe it, and how those conditions remain stable most of the time. But when those conditions shift even slightly, the moon looks different. And that difference reveals something about how it actually behaves. Now consider what this means for being on the moon during such an event. If you were standing on the lunar surface during a lunar eclipse, you wouldn't see the same thing we see from Earth. You wouldn't see the moon darkening. You would see the Earth. The Earth would move into position, blocking the sun, and the surface around you would dim, the sky would darken, and in place of the sun you would see a ring of light around the Earth's edge, the atmosphere glowing faintly, casting that reddish light onto the surface. It would be a very different perspective, not a distant observation, but a direct experience of the alignment between the sun, Earth, and Moon. And again, that alignment doesn't introduce new dangers, but it emphasizes how dependent the Moon's environment is on light, on position, on what is between it and the sun. Because without that light, everything changes. Temperature, visibility, energy, all tied to whether sunlight is present or not. So while a lunar eclipse might seem like a simple visual event from Earth, it reflects deeper aspects of how the Moon exists in space, how it interacts with light, how shadows behave, how conditions shift when that light is removed, and how quickly those shifts can occur. It's another example of how something that appears calm and predictable can reveal a more complex reality when you look at it from a different angle, not because it becomes dangerous in a sudden way, but because it shows you how much of what you see depends on conditions you don't usually think about. And once you start noticing that, once you begin to see how light, shadow, and position influence the Moon's appearance, it becomes easier to understand that there are many aspects of the Moon that are not immediately visible. Not just the far side, not just the processes happening on its surface. Long before the Moon started to feel like a place filled with subtle risks and hidden challenges, it existed in human imagination as something distant and unreachable. A destination, yes, but also a symbol. And when the first missions were planned, when humans prepared to leave Earth and step onto that surface, the focus was often on the achievement itself. Getting there, landing, walking, returning. Those were the visible milestones, the parts that would be remembered. But behind those moments there was a constant awareness of something else. Not a single danger, not one obvious threat, but a collection of conditions that had never been experienced directly before. Because no matter how much preparation took place on Earth, no matter how carefully systems were tested and refined, the Moon remained an environment that could not be fully recreated, which meant that every mission carried a level of uncertainty, not dramatic, not reckless, but present, always in the background. The astronauts who travelled to the Moon were trained extensively. They practiced movements in simulated low gravity, learned how to operate equipment while wearing suits, studied the terrain, the procedures, the sequences of events that would guide them through each phase of the mission. Everything was planned in detail. And yet, the moment they arrived, the environment introduced variables that could not be completely predicted. Take the landing itself. Bringing a spacecraft down onto the Moon is not the same as landing on Earth. There is no atmosphere to slow the descent, no air resistance. Everything depends on controlled thrust, precise adjustments. The spacecraft must reduce its speed using engines alone, balancing against gravity in a way that requires constant attention. And then there's the surface, from orbit. The landing sites appeared relatively smooth, but as the Apollo 11 module approached the surface, the astronauts realized that the area was more uneven than expected. Covered in rocks, cratered, not ideal for landing. Neil Armstrong had to take manual control, guiding the module to a safer location while fuel levels dropped. That moment, often remembered as a calm and controlled adjustment, carried a quiet urgency. There was limited time, limited fuel, no margin for extended hesitation, and yet it was handled with precision. The landing succeeded, but it revealed something important. Even with preparation, the Moon could still present surprises. Then came the surface operations. Walking on the Moon, as we've discussed, is not the same as walking on Earth. The reduced gravity changes how you move. The suit restricts motion. Every step requires awareness. Astronauts described the experience as both manageable and unfamiliar. It took time to adjust, to find a rhythm, to move efficiently without overcompensating. And even then, falls happened. Not dramatic falls, but moments where balance shifted unexpectedly. Recovering from those falls required effort, especially with the suit limiting flexibility. And while the lower gravity reduced the force of impact, it didn't remove the challenge of getting back up. Now consider the suit itself. It wasn't just clothing. It was a complete life support system, providing oxygen, maintaining pressure, regulating temperature, protecting against radiation and micrometeorites. Every function that the environment on Earth provides naturally had to be replicated inside that suit, and that meant that the suit had to work continuously, without failure. Even a small issue, a leak, a malfunction, could become serious very quickly, which is why astronauts monitored their systems constantly, checking readings, confirming pressure, ensuring that everything remained within safe limits. There was no moment where they could simply ignore it, because the environment didn't allow for that. The dust, as we explored earlier, introduced another layer of difficulty. It clung to suits, collected in joints, affected visibility, and it followed the astronauts back into the lunar module. Inside, it became a different kind of problem. Floating briefly in the air before settling, it created irritation. Not severe, but noticeable. And again, this was after short exposure. Longer stays would have amplified the effect. Then there's the matter of time. Not just how long the missions lasted, but how time felt in that environment. On the Moon, there is no natural cycle of day and night in the way we experience it on Earth. The sun moves slowly across the sky over the course of 2 weeks, which means that during the missions the astronauts operated in continuous daylight. No sunset. No natural signal that the day is ending. Everything is managed by schedules, by mission control, by systems designed to keep track of time. That might seem like a small detail, but it changes perception. Without the usual cues, your sense of progression shifts. You rely more on external structure than on the environment itself, and that adds to the overall experience. Because you are not just adapting to physical conditions, you're adapting to a different way of experiencing time and space. Communication too was constant but not instantaneous. There was a slight delay between Earth and the Moon, not long, just over a second, but enough to be noticeable, enough to remind you that you are not in immediate contact, that every message takes time to travel, that responses are not immediate, and while this didn't prevent communication, it changed its rhythm. It required patience, clarity, a different way of interacting. Then there's the broader context. Being on the Moon meant being very far from Earth, not just physically, but in terms of support. On Earth, if something goes wrong, there are systems in place. People, infrastructure, resources. On the Moon, everything you need is what you brought with you. There is no immediate backup, no quick assistance. Every solution must come from within the mission itself, which means that problem solving becomes more focused, more immediate. There's no option to wait for external help. You're already as far from it as you can reasonably be. And that awareness, even if it's not always at the front of your mind, is part of the experience. It shapes how you approach tasks, how you manage risk, how you respond to unexpected situations. Now, it's important to recognize that these missions were successful. Astronauts landed, conducted experiments, collected samples, and returned safely. The systems worked, the planning was effective, but that success doesn't mean the environment was safe. It means the risks were understood and managed, carefully, continuously. And even then, there were moments where things didn't go exactly as planned. Equipment issues, unexpected conditions, situations that required adjustment, handled calmly but still present. Which brings us back to the idea of hidden risks, not dangers that are obvious or dramatic, but conditions that require constant attention, systems that must function without interruption, environments that do not allow for error. From Earth, the missions can look smooth, controlled, almost routine in hindsight, but that perspective comes from seeing the outcome, not the ongoing process, not the continuous awareness required to operate in that environment. And that's what makes the Moon different. It doesn't present its risks loudly. It doesn't create immediate obstacles that force you to react. Instead, it creates conditions where everything must be managed carefully. where small issues can become larger if not addressed, where attention and preparation are as important as the physical systems themselves. It's a place where success depends not just on technology, but on understanding, on recognizing what the environment requires and adapting to it. And as you begin to think about those experiences, not just the achievements, but the conditions they were achieved in, the moon becomes something more than a destination. It becomes a place that demands a certain kind of awareness, a place where the usual assumptions about safety and comfort don't apply, and where the experience of being there is shaped as much by what you don't immediately notice as by what you do. Try to picture a place where nothing interrupts your thoughts. No background hum, no distant traffic, no shifting wind, no birds, no subtle sounds that remind you the world is still moving around you. Just stillness. Not the kind of quiet you get at night on Earth, where there is always something faint in the distance, but a complete absence of external sound. Now imagine staying there, not for a few minutes, but for hours, days. Long enough for that silence to stop feeling unusual and start feeling like the normal state of things. That's where the psychological side of the moon begins to take shape. Because while the physical risks are easier to describe, the absence of familiar sensory input affects you in ways that are less obvious at first. On Earth, your mind is constantly anchored by subtle signals. Sound is one of the most important. Even when you're not paying attention to it, it's there, helping you understand space, distance, activity. It tells you when something moves, when something changes, when something exists beyond your immediate field of vision. Remove that, and your awareness narrows. You rely almost entirely on what you can see and what you can physically feel. And even that feels different, because the moon's environment doesn't offer much variation. The surface stretches out in shades of grey. The sky is always black, even during the day. There are no clouds moving across it, no shifting colours, no gradual changes in light beyond the position of the sun. Everything is steady, unchanging, at least on the timescales you experience directly. That kind of visual consistency can feel calm at first, but over time it can also feel limiting. Because your brain is used to variation, it expects change. It looks for patterns that evolve, for movement that signals the passage of time. Without those cues, time itself can begin to feel different. Not slower exactly, but less defined. You don't have the same markers to separate one moment from the next. No sunrise or sunset in the familiar sense. No shifting sky to indicate progression. Instead, you rely on schedules, on clocks, on systems that tell you what time it is, rather than sensing it from your surroundings. That separation can feel subtle, but it adds up. Because your experience of time is not just about measurement, it's about perception. And when perception changes, your sense of progression changes with it. Then there's the matter of distance, not just physical distance from Earth, but the feeling of being removed from everything familiar. On Earth, even when you're alone, you're still within a system. There are people nearby, infrastructure, resources, a sense that if something happens, there are layers of support around you. On the moon, that sense is different. You are aware, even if only in the background of your thoughts, that you are far from all of that everything you need is contained within your immediate environment, your suit, your habitat, your equipment. There is no outside support in the usual sense. No immediate assistance, no quick access to anything beyond what is already there. That awareness doesn't have to feel overwhelming, but it is present. A quiet understanding that changes how you think about your situation. It makes the environment feel more self-contained, more isolated. Communication with Earth remains possible, of course, but it is not the same as being there. There is a delay, a small one, but enough to remind you that you are not in direct, immediate contact. Conversations have a different rhythm. You speak, you wait, you listen. That pause, repeated over time, reinforces the distance. It becomes part of the experience. Now consider the combination of all these factors. Silence, limited visual variation, altered perception of time, distance from Earth. Each one on its own might not feel significant, but together they create an environment that is very different from anything we are used to. And that difference requires adjustment. Not just physically, but mentally. Astronauts are trained for this. They prepare for isolation. They practice working in confined environments. They develop routines that help maintain focus and stability. But training can only go so far, because the actual experience includes elements that are difficult to simulate fully. The knowledge that you are on another world. The awareness that the environment outside your immediate shelter is not just unfamiliar, but actively hostile. The realization that stepping outside requires complete reliance on your equipment. All of this shapes how you think and feel, even if it remains in the background. There's also the effect of scale. On the Moon, distances can be deceptive. With no atmosphere to create depth cues like haze or perspective, objects can appear closer or farther than they actually are. The horizon is closer due to the smaller size of the Moon, which changes how you perceive space. Everything can feel slightly compressed, slightly different from what you expect. That can add to the sense of unfamiliarity, a feeling that the environment doesn't behave in the usual way. And when your surroundings don't match your expectations, your mind has to work a little harder to interpret them. That effort, repeated over time, contributes to mental fatigue, not in a dramatic way, but gradually. Then there's the absence of life. No plants, no animals, no signs of biological activity. On Earth, even in the most remote places, there is usually some indication of life. A bird in the distance, a plant growing in unexpected places. Something that reminds you that the environment is part of a larger system. On the Moon, there is none of that. It is completely inert. Every surface is rock or dust. Every change is the result of physical processes, not biological ones. That absence can feel neutral at first, but over time, it can also feel stark. Because it removes another layer of familiarity, another connection to what you're used to. Now, none of this means that being on the Moon would be overwhelming in a negative sense. People adapt, they adjust, they find ways to create structure, to maintain focus, to work within the environment. But the psychological aspect is still there, part of the overall experience. And it's one of the reasons why long-term missions require careful planning, not just for physical safety, but for mental well-being. Routines become important. Tasks provide structure. Communication, even with its delays, helps maintain connection. All of these elements contribute to managing the effects of isolation. Because isolation is not just about being alone. It's about being separated from familiar systems, from the cues and signals that your mind uses to orient itself. And on the Moon, many of those cues are either absent or different, which means that your sense of place, of time, of connection, all shift slightly. Not enough to disrupt you immediately, but enough to change how the experience feels over time. It's interesting how this connects back to the earlier idea of silence, not just as an absence of sound, but as an absence of feedback, a lack of external input that your mind normally uses without thinking about it. And when that input is reduced, your internal processes become more noticeable. Your thoughts feel clearer, more present, because there is less competing with them. That can be calming, but it can also be intense, depending on how long you remain in that environment. Consider how naturally your day unfolds on Earth without you ever needing to think about it. Morning arrives, not because you checked a clock, but because light gradually fills the sky. Your body responds before your mind fully catches up. There's a sense of progression built into the environment itself. Midday feels different from evening, and evening feels different from night. Even if you ignore the time, you still feel it passing. Now place yourself on the Moon and remove those signals, not all at once, but gently, piece by piece. What you're left with is something that still measures time perfectly, but doesn't feel like time in the same way. Because on the Moon, time does not announce itself. It doesn't move around you. It doesn't shift the sky in familiar ways. It simply exists quietly, while everything else stays almost unchanged. Start with something simple. A day. On Earth, a day is about 24 hours. That rhythm is so deeply built into how we live that it feels natural. You wake, you move through your routine, and the environment reinforces that cycle constantly. On the Moon, a single day, meaning one full cycle from sunrise to sunrise, lasts about 29.5 Earth days. That means that once the sun rises over a location on the Moon, it stays there for roughly 2 weeks. 2 weeks of continuous daylight. Then, just as slowly it sets, and that location enters about 2 weeks of darkness. Not a night that lasts hours, a night that lasts half a month. Now imagine experiencing that directly. There is no quick sunrise to begin your day, no sunset to signal its end. The sun moves so slowly across the sky that over the course of a few hours you might not notice any change at all. The shadows shift, but only slightly. The light remains constant, and because of that your sense of time begins to detach from the environment. You can no longer rely on the sky to tell you where you are in the day. Instead, you rely on clocks, schedules, artificial systems that define when something starts and when it ends. And while those systems are precise, they don't replace the feeling of time. They measure it. They don't express it. This creates a subtle disorientation. Not confusion exactly, but a lack of natural cues. You might know that it's morning because your schedule says so, but the environment around you doesn't confirm it. The light hasn't changed. The sky hasn't shifted. Everything looks almost exactly as it did hours ago, and that can make time feel less anchored, less connected to your surroundings. Then there's another layer to consider. On the Moon, time actually passes at a slightly different rate than it does on Earth. Not in a way you would notice directly, but in a measurable physical sense, because time is affected by gravity. This idea comes from Einstein's theory of relativity. The stronger the gravitational field, the slower time passes relative to a weaker one. Earth, being more massive, has stronger gravity than the Moon, so time on the Moon moves slightly faster. Not by much, just a tiny fraction. But it's real. If you had 2 perfectly synchronized clocks, one on Earth and one on the Moon, over time, the lunar clock would move ahead. It would tick just a little faster. Now, in practical terms, this difference is extremely small. You wouldn't feel it, you wouldn't perceive it, but it's another reminder that time is not as fixed as it seems. It depends on where you are. And the Moon is a place where even that fundamental aspect of reality behaves slightly differently. Now combine that physical difference with the perceptual changes. Long days, long nights, no atmosphere to soften light, no gradual transitions, and you start to get a sense of how unusual the experience becomes, because your internal sense of time, your circadian rhythm, is still based on a roughly 24-hour cycle. Your body expects variation, light and dark, activity and rest, but the environment doesn't provide those cues in the same way, so your body and your surroundings fall out of sync, which is why any long-term presence on the Moon would require artificial cycles, controlled lighting, structured schedules, systems designed to simulate the day-night rhythm your body expects. Without that, maintaining a regular pattern of sleep and wakefulness becomes difficult. Not impossible, but less natural, and that effort adds to the overall experience. Then there's the psychological side of this. Time as we experience it is closely tied to change. We notice time passing because things around us change. The position of the sun, the colour of the sky, the movement of shadows. On the Moon, those changes happen, but they happen slowly. So slowly that, in the moment, they can feel almost absent, which can make time feel stretched. Not in the sense that it's moving slower, but in the sense that there are fewer markers to divide it. Moments blend together more easily. Hours feel less distinct, and without clear transitions, it becomes easier to lose track of how much time has passed. Now, this doesn't mean that time itself is behaving unpredictably. It's still moving forward at a steady rate, but your experience of it becomes less structured, less defined by external signals, and more dependent on internal awareness and artificial systems. There's also an interesting effect when you consider how light behaves. On Earth, even at night, there's usually some level of ambient light. Moonlight, starlight, reflections from the atmosphere. On the Moon, when you're in darkness, it is deep. Not absolute, but much closer to it. And when you're in sunlight, it is direct, bright, unfiltered. There is no gradual transition between these states, which means that the shift from light to dark or dark to light feels more abrupt when it does occur, even though the overall cycle is long. So time on the Moon is not just longer in terms of day and night, it's also more extreme in how those phases are experienced, and that combination, long durations with sharp contrasts, creates a different rhythm, one that doesn't match what your body is used to. Now think about how all of this connects to the broader experience of being there. You're already in an environment that is silent, isolated, visually limited, and now time itself feels less anchored, less tied to what you can see and sense around you. That can create a feeling of detachment, not from reality, but from the usual markers that define it, which is why structure becomes so important. Routines, schedules, defined periods of work and rest. All of these act as substitutes for the natural cues that are missing. They provide a framework that helps maintain a sense of progression, a way to divide time into manageable parts, because without that framework the experience can become more fluid, less segmented, and while that might sound calm, it can also be disorienting. Now from Earth, none of this is visible. You see the Moon as a steady presence. You don't see the slow movement of the Sun across its surface. You don't feel the length of its days or nights. You don't experience the way time is perceived there. But once you begin to think about it, once you imagine being in that environment, the Moon becomes something more than just a place with different physical conditions. It becomes a place where your relationship with time itself changes. Not dramatically, not in a way that disrupts everything at once, but gradually, subtly, in ways that require adjustment. And that adjustment is part of what makes the Moon such a unique environment, because it's not just about surviving the conditions, it's about adapting to a different rhythm, a different way of experiencing the passage of time, and that rhythm doesn't just affect individuals, it would shape how any long-term presence on the Moon operates, how people live, how they organise their days, how they interact with the environment. Picture for a moment not a brief visit to the Moon, but staying there. Not stepping outside for a few hours, collecting samples and returning safely to a spacecraft, but actually living there. Waking up there, eating, working, resting, repeating the same routines day after day, in a place that was never meant to support life on its own. The idea of a lunar base often sounds clean and controlled, a structure placed on the surface, carefully designed, filled with systems that provide everything needed: oxygen, temperature control, energy, communication. From a distance, it feels manageable, like building in an unusual location, but still building something stable. But when you bring together everything we've been exploring, the lack of air, the temperature extremes, the dust, the radiation, the constant impacts, the low gravity, and the psychological effects, the idea of living there begins to feel less like settling into a place and more like continuously maintaining a balance. Because nothing about the Moon supports you naturally. Everything that keeps you alive must be created, maintained, and protected. Start with the habitat itself. On Earth, a building separates you from the outside environment, but it doesn't need to do everything. The air outside is breathable. The temperature, while variable, is within a range that can be managed with relatively simple systems. The ground is stable. On the Moon, the habitat becomes your entire environment. It must provide air, pressure, temperature, radiation shielding, and protection from impacts. It must function continuously, without interruption. Because if it stops, even briefly, The outside conditions take over immediately. There's no buffer, no gradual transition. That means redundancy becomes essential. Systems need backups, and those backups need backups. Because failure is not something you can easily recover from. Now consider how those systems operate over time. They don't remain perfect. Filters wear out, seals degrade, components experience stress from temperature changes and constant use. And as we discussed earlier, lunar dust finds its way into everything. It settles on surfaces, gets into joints, interferes with moving parts. Even with careful design, it becomes part of the environment inside and outside the habitat. Which means maintenance is not occasional, it's constant, a routine part of daily life. Checking systems, replacing parts, cleaning surfaces, ensuring that everything continues to function as expected. Because if you stop paying attention, problems can develop quietly. And on the moon, quiet problems are often the ones that matter most. Then there's energy. On Earth, energy is widely available. Power grids, fuel sources, renewable systems, all connected and supported by large-scale infrastructure. On the moon, energy must be generated locally, most likely through solar panels, which works well during the long lunar day. But during the long night, those panels produce nothing. For about 2 weeks, that means energy must be stored in batteries or other systems, enough to last through the entire period of darkness, and those storage systems must remain reliable, because if energy runs out, other systems begin to fail. Temperature control, air circulation, communication, everything depends on power, so managing energy becomes a central concern, not just generating it, but storing it, distributing it, using it efficiently. Every action has an energy cost, and that cost must be accounted for. Now think about movement outside the habitat. Every time someone steps onto the lunar surface, they're entering an environment that requires full protection. The suit becomes their life support system, and just like the habitat, it must function continuously. It must maintain pressure, supply oxygen, regulate temperature, and protect against radiation and impacts. And it must do all of this while allowing movement, which is already restricted, so every excursion outside is planned, carefully, time-limited, with clear objectives, because the longer you remain outside, the more you rely on systems that must not fail. Even small issues become important. A slight reduction in mobility, a minor problem with a seal, a small increase in dust accumulation. Each one requires attention. Now extend this over longer periods, days, weeks, months. Living on the moon is not about avoiding danger entirely. It's about managing it continuously. Because the danger is not concentrated in one place. It's everywhere, in the environment itself. Which means that safety is not a single condition. It's an ongoing process, maintained through awareness, preparation, and constant adjustment. There's also the matter of supplies. Everything needed to support life must either be brought from Earth or produced on the moon. Water, food, air, materials. Each one requires planning, storage, management. Some resources might be extracted locally, for example, water ice in certain regions of the moon, but that introduces additional systems, mining, processing, purification. Each step adds complexity, and each system becomes another point that must be maintained. Then there's communication. Even with advanced systems, the moon remains distant. Messages take time to travel. Support from Earth is not immediate. Decisions often need to be made locally, which means that the people living there must be capable of handling situations independently, diagnosing problems, implementing solutions, without waiting for detailed instructions from Earth. That level of autonomy is different from what we're used to, and it adds another layer to the experience because it requires confidence, training, and the ability to remain calm under conditions that are not forgiving. Now consider the long-term effects of low gravity. Over extended periods, the body changes. Muscles weaken, bones lose density. Even with exercise, these effects are difficult to prevent entirely. So living on the moon means living in a state where your body is gradually adapting to a different environment. An environment that is not ideal for long-term human health, which means that any colony would need to account for that. Through exercise routines, through medical monitoring, possibly through artificial gravity in some form. All of these add complexity, and complexity requires management. There's also the psychological side. We touched on isolation earlier, but in a long-term setting it becomes more significant. You are living in a confined space, with a small group of people, in an environment that does not change much visually. The same landscape, the same interior, the same routines, day after day. That can feel stable, but it can also feel repetitive, and maintaining mental well-being becomes just as important as maintaining physical systems, which means creating variety, structure, opportunities for rest and relaxation, even in a place where the environment itself does not provide those things naturally. Now, none of this means that living on the moon is impossible. It means that it is demanding, in a consistent, ongoing way. It requires attention to detail, a willingness to adapt, and understanding that the environment does not support you unless you actively manage it. From Earth, the idea of a lunar colony can feel exciting, a step forward, a new place to explore and inhabit, and it is all of those things. But it is also a place where the margin for error is very small, where systems must function reliably, where awareness must be continuous, and where the environment does not provide second chances easily. It's not a place where you can relax into the surroundings. It's a place where you create a safe space within an unsafe environment, and maintain it, every day. Which brings us back to the broader idea we've been building. The moon looks calm, it appears stable, but living there reveals how much effort is required to maintain that stability. Not because the moon changes suddenly, but because it doesn't change in ways that help you. It remains exactly what it is, and you must adapt to it, continuously. At first glance, the moon gives the impression of complete stillness. No shifting landscapes, no moving plates, no signs of ongoing activity in the way we're used to seeing on Earth. There are no oceans moving across its surface, no winds reshaping the terrain, no vegetation growing or changing. Everything appears fixed, almost frozen in place, as if time itself has slowed down there. And for a long time, it was easy to assume that the moon was completely inactive, a world that had cooled, settled, and stopped changing in any meaningful way. But that assumption doesn't hold up once you begin to look more closely, because the moon does move, not constantly, not dramatically, but enough to matter. The surface experiences what are known as moonquakes, small seismic events that reveal that the moon is not entirely still beneath its surface. Now, these are not the same as earthquakes. On Earth, quakes are often caused by the movement of tectonic plates, large sections of the crust shifting against each other, building up stress and releasing it suddenly. The moon doesn't have active plate tectonics in the same way. Its internal structure is different. Its surface is not divided into moving plates that constantly interact, but it still experiences stress, and that stress comes from several sources. One of the most interesting is the gravitational interaction with Earth. Just as the moon pulls on Earth's oceans to create tides, Earth also pulls on the moon. This creates what are known as tidal stresses within the lunar interior. The moon is not perfectly rigid. It flexes slightly as it orbits Earth. That flexing is small, but over time it builds stress within the crust, and occasionally that stress is released, as a moonquake. These tidal moonquakes tend to occur at regular intervals, linked to the moon's orbit. They are predictable, part of the ongoing interaction between the Earth and the moon. Then there are thermal moonquakes. These are caused by the extreme temperature changes we discussed earlier. During the long lunar day, the surface heats up. During the long night, it cools down. This repeated expansion and contraction creates stress in the outer layers of the moon, and sometimes that stress is released as small seismic events. Again, not dramatic, but present. Then there's another type, shallow moonquakes. These are less predictable and can be more significant. They originate closer to the surface and can last longer than you might expect. In fact, one of the surprising things about moonquakes is how long they can continue. On Earth, earthquakes tend to release energy quickly. They shake, and then they stop. On the Moon, because the material is different and there is no water to dampen vibrations, seismic waves can travel for much longer. A moonquake can last for several minutes. The surface can continue to vibrate gently, without the rapid dissipation we see on Earth. That difference comes from the Moon's dry, rigid structure. Without water or softer materials to absorb energy, vibrations persist. They echo, not loudly, not in a way you would hear in the usual sense, but in a way that would be detectable through instruments, and potentially noticeable if you were standing on the surface. Now, the Apollo missions actually placed seismometers on the Moon. These instruments recorded moonquakes and provided valuable data about the Moon's interior. They showed that the Moon is not entirely inactive, that there are still processes happening beneath the surface, even if they are subtle, even if they occur less frequently than on Earth. And this adds another layer to our understanding of the Moon, because it's not just a static environment shaped entirely by past events. It still experiences change, slow, intermittent, but real. Now consider what this means for being on the Moon. A moonquake is not likely to be as immediately destructive as a strong earthquake on Earth. The forces involved are generally smaller, but the environment amplifies certain effects. Structures on the Moon would need to account for these vibrations, not just the strength of the quake, but its duration. A prolonged vibration, even if it's not very intense, can place stress on materials and systems. Over time, repeated events could contribute to wear, small shifts, minor adjustments that need to be monitored, and because the Moon's surface is covered in loose regolith, vibrations can affect how that material settles. Dust can shift, surfaces can become slightly less stable, again, not dramatic changes, but enough to require attention. There's also the matter of predictability. Some moonquakes, like tidal ones, follow a pattern. Others do not, which means that while you can anticipate certain events, you cannot account for all of them. There is always a level of uncertainty. Now from Earth, none of this is visible. The Moon looks completely still, unchanging. You don't see the subtle flexing caused by gravitational forces. You don't see the internal stresses building and releasing. You don't feel the surface vibrations. But they are there, part of the Moon's behaviour. And once you begin to think about it, the idea of the Moon as a perfectly stable, unchanging place starts to shift. It's stable in a broad sense. It doesn't have the constant activity of Earth, but it is not completely static. It moves, quietly, occasionally, in ways that are easy to overlook, and that's consistent with everything else we've explored. The Moon's risks are not always obvious. They don't always present themselves in dramatic ways. They're often subtle, persistent, part of the environment rather than separate from it. Moonquakes fit into that pattern. They are not the defining feature of the Moon, but they are part of it. A reminder that even in a place that appears still, there can be motion. Even in a place that seems quiet, there can be activity. And understanding that helps build a more complete picture. Not just of what the Moon looks like, but of how it behaves. Because behaviour matters, especially when you imagine being there, living there, relying on the stability of the ground beneath you, and knowing that from time to time that ground can shift, gently but noticeably. It's another example of how the Moon challenges assumptions. It looks calm, it feels distant, but the closer you get, the more you realise that it is not as simple as it appears. Not dangerous in a single, obvious way, but complex, layered, defined by multiple factors that interact in ways that require attention. And when you begin to see all of those factors together, the surface conditions, the dust, the radiation, the impacts, the gravity, the time, and now the subtle movement beneath your feet, the Moon becomes something more than just a destination. It becomes a system. Long before the Moon became the steady presence we see in the night sky, before it settled into its familiar orbit and quiet rhythm, it began in a way that was anything but calm. not through slow accumulation, not through gentle formation, but through an event so large that it reshaped the entire early Earth. To understand that beginning, you have to imagine the solar system at a time when it was far less stable than it is now. Planets were still forming, orbits were still settling, large bodies moved through space with paths that had not yet become predictable. Collisions were not rare. They were part of the process, and at some point around 4.5 billion years ago, one of those collisions involved the early Earth. A body roughly the size of Mars, often referred to as Theia, collided with our planet. Not a glancing contact, not a small impact, but a massive high-energy collision that released an extraordinary amount of force. Now, it's important to picture this not as a simple crash, but as an interaction between two large, partially molten worlds. The early Earth was hotter than it is now. Its surface was not fully solid, and when Theia struck, the energy involved was enough to melt, vaporize, and eject material from both bodies. Debris was thrown into space, not just small fragments, but vast amounts of rock and molten material. For a time, the Earth was surrounded by a disk of this debris, a ring of material orbiting the planet, and within that ring, something began to happen. The debris started to come together, not instantly, but gradually. Fragments collided, stuck, merged. Gravity pulled them closer. Over time, this material coalesced into a single body, the Moon. So the Moon was not formed independently and later captured by Earth. It was created from the aftermath of a collision, from material that once belonged to the Earth and the impacting body. Which means that, in a very real sense, the Moon and Earth share a common origin. They are connected not just by gravity, but by composition, by history. Now, this origin explains some of the Moon's characteristics. Its composition is similar to Earth's outer layers. It lacks certain elements that would be expected if it had formed elsewhere. Its structure reflects the conditions of that early high-energy environment. But beyond the scientific details, what stands out is the nature of the event itself. The Moon exists because of a catastrophic impact, a moment of extreme violence that reshaped a planet and created a new object in orbit around it. And that sets the tone for how we think about the Moon's history. Because from the very beginning, it was shaped by forces that are not gentle. Forces that involve energy, motion, and interaction on a massive scale. Now, after its formation, the Moon was much closer to Earth than it is today. Significantly closer, which means that its gravitational influence was stronger. Tides on Earth would have been more extreme, the interaction between the two bodies more intense. Over time, as we discussed earlier, the Moon moved away, the system evolved. But in those early stages, the relationship between Earth and the Moon was very different, more dynamic, more active, and the Moon itself was not the cold, quiet body we see now. It was hotter, possibly covered in a global magma ocean, a surface of molten rock that slowly cooled and solidified. As it cooled, its internal structure formed, a crust developed, layers settled, and over time the Moon transitioned from that early, active state to the more stable condition we observe today. But the transition was not immediate. It took time, millions of years, during which the Moon continued to be affected by impacts, by internal processes, by the same forces that shaped the early solar system, and those processes left marks, craters, basins, surface features that remain visible today. So when you look at the Moon now, you're not just seeing its current state, you're seeing the result of its entire history. From its formation in a massive collision to its gradual cooling and evolution. Now, there's an interesting contrast here. The Moon appears calm, stable, unchanging. But its origin is anything but that. It began with one of the most energetic events possible, a collision between planetary bodies, and that contrast highlights something important. The current state of an object does not always reflect how it came to be. Stability can emerge from instability. Calm can follow chaos. And the Moon is a clear example of that. But that origin also has implications. because it reminds us that the moon is part of a dynamic system, one that has experienced significant changes in the past, and while those changes are not happening at the same scale today, the system is still evolving, still moving, still interacting. The Earth and Moon continue to influence each other, through gravity, through motion, through the transfer of energy, and that connection traces all the way back to that initial collision. Now, from a human perspective, this origin might feel distant, something that happened so long ago that it has no direct impact on us now, but it shapes everything that follows. The moon's size, its distance from Earth, its gravitational influence. All of these are tied to how it formed. If that collision had been different, if Theia had struck at a different angle, or with different energy, the result could have been very different. The moon might not exist at all, or it might be smaller, larger, closer, farther away. Each of those possibilities would change the Earth in significant ways. Tides, rotation, climate stability, all influenced by the presence and characteristics of the moon. So the moon's origin is not just a story about the past, it's a foundation for the present, a key factor in how the Earth-Moon system behaves today, and understanding that origin adds depth to how we think about the moon. It's not just a passive object, it's the result of a process, a sequence of events that shaped its structure and its relationship with Earth. Now there's also something else to consider. The early solar system was full of collisions, large bodies interacting, merging, breaking apart. That environment has calmed significantly over time, but it has not become completely static. Impacts still occur, objects still move, the difference is scale and frequency. Which means that while the moon's formation was an extreme event, it is part of a broader pattern of how planetary systems develop, and that pattern includes both creation and destruction, both formation and change, which brings us back to the idea of the moon as something more complex than it appears. It looks calm, it feels familiar, but its history is built on events that are anything but gentle, and that history is still visible in the structure of the moon, in the features on its surface, in the way it interacts with Earth. It's a reminder that what we see now is just one moment in a much longer story, a story that began with a collision and continues through subtle interactions that shape both the moon and the Earth. And when you start to see it that way, the moon becomes something more than a distant light. It becomes part of an ongoing system, one that connects past, present, and future in ways that are not always immediately obvious. Because even now, even in its current stable state, the moon continues to influence Earth, not just through tides, but through the balance it helps maintain. A balance that, if changed, would affect more than just the ocean. It would reach into the very conditions that make life on Earth what it is today. It's easy to take for granted that the moon always looks the same. You glance up and there it is, with its familiar pattern of dark plains and lighter highlands, arranged in a way that never seems to change. Over time, that image becomes so consistent that it stops feeling unusual. But if you pause and think about it, there's something quietly strange about that consistency. Because the moon is not standing still, it's moving, constantly orbiting Earth. And yet, despite that motion, it keeps the same face turned toward us. That's not coincidence. That's not random alignment. It's the result of a long process known as gravitational locking, or tidal locking. And like many things about the moon, it sounds simple at first, but becomes more interesting the closer you look. To understand it, imagine the moon not as a fixed object, but as something that can rotate. Like Earth. Earth spins on its axis once every 24 hours. The moon also rotates, but it does so in a very specific way. It rotates once on its axis in the same amount of time it takes to orbit Earth, about 27.3 days. That synchronization is what keeps the same side facing us. As the moon moves around Earth, it turns just enough to keep that alignment. If it didn't rotate at all, we would see different sides of it over time. If it rotated faster or slower, the view would shift. But because the rotation and the orbit match, the same hemisphere remains visible. Now the interesting part is how it got that way, because it wasn't always like this. Early in its history, the moon likely rotated at a different rate. Not synchronized, its rotation gradually slowed over time, and the reason for that has to do with gravity. Earth's gravity pulls on the moon. Not evenly, but slightly more strongly on the side closest to Earth. This creates a small stretching effect, a tidal bulge. The moon becomes slightly elongated along the line pointing toward Earth. Now, if the moon is rotating, that bulge doesn't stay perfectly aligned with Earth. It shifts slightly ahead or behind, depending on the rotation, and when that happens, Earth's gravity pulls on the bulge, trying to bring it back into alignment. That pull creates friction within the moon's interior, and over time, that friction slows the rotation, gradually, very gradually, until eventually the rotation slows enough that the bulge stays aligned with Earth. At that point, the system reaches a stable configuration. The moon rotates once per orbit, and the same side always faces Earth. This process took millions of years. It wasn't sudden. It was the result of continuous interaction between the two bodies, a slow adjustment toward balance. Now this might sound like a purely mechanical detail, a feature of motion, but it has real consequences, because the fact that we only see one side of the moon shapes how we understand it. For most of human history, the far side was completely unknown. Everything we knew about the moon came from observing that single visible hemisphere. And as we discussed earlier, that led to an incomplete picture. Only with the advent of spacecraft did we finally see the far side, and discover how different it is, more heavily cratered, less covered in the dark plains we're familiar with. But beyond observation, tidal locking also affects how the moon interacts with Earth. The constant orientation means that the gravitational relationship between the two bodies is stable, predictable. The tidal forces we experience, the patterns of motion, all depend on this alignment. If the moon were not tidally locked, the interaction would be more complex. The gravitational pull would vary in ways that are harder to predict. But because the system has settled into this configuration, it behaves in a consistent way. Now, there's also a subtle extension of this idea. Because tidal locking is not unique to the moon. It happens throughout the solar system. Many moons are tidally locked to their planets. Even Mercury, for example, has a kind of tidal relationship with the Sun, though not a perfect one-to-one lock. It's a common outcome of gravitational interaction over long periods. Bodies influence each other, energy is transferred, rotation slows or adjusts, and eventually stable patterns emerge. So in that sense, the moon is following a broader pattern, but from our perspective it feels unique, because it shapes how we see the moon every day. Now there's something else worth considering. The moon is tidally locked to Earth, but Earth is not tidally locked to the moon, at least not yet. Earth still rotates independently, but as we mentioned earlier, the moon's gravitational pull is gradually slowing that rotation, very slowly, over extremely long timescales. If you extend that process far enough into the future, something interesting happens. Earth could become tidally locked to the moon, meaning the same side of Earth would always face the moon, and the same side of the moon would face Earth, a mutual locking. At that point, the system would reach a different kind of equilibrium, stable, but different from what we experience now. Of course, that is far beyond any timescale that affects us directly, but it illustrates how these processes evolve, how systems change over time, even when they appear stable in the moment. Now, from a human perspective, tidal locking contributes to the moon's familiarity. Because we always see the same face, it becomes recognizable, predictable, a constant reference in the sky. But that familiarity can also be misleading. It can make the moon feel simpler than it is, more uniform, because we're only seeing one part of it, and that connects back to a broader theme we've been exploring, the difference between what is visible and what is actually there. The moon shows us one side, consistently, But that doesn't mean the rest is not important, or that it behaves in the same way. It's simply hidden from our direct view. And that hidden portion, along with all the processes we've discussed, adds depth to how we understand the moon. Now there's also a physical implication to this constant orientation. Because one side of the moon always faces Earth, it also means that one side is always facing away. And as we touched on earlier, that has consequences for communication, for observation, for how we interact with the moon as a place. But it also reinforces the idea that position matters, orientation matters. Where you are on the moon changes your relationship with Earth, changes what you can see, what you can connect to, and how you experience the environment. So tidal locking is not just a detail about motion, it's part of the structure of the Earth-Moon system, a feature that influences perception, interaction, and behaviour. And like many aspects of the moon, it's easy to overlook. Because it's consistent, it doesn't change from one night to the next, it doesn't draw attention to itself, it simply is. But once you start to think about it, once you consider how that alignment came to be, and what it means for the system as a whole, it becomes another piece of the larger picture. Another example of how the moon is shaped by forces that operate over long periods. Forces that create stability, but also reveal that stability is the result of continuous interaction. And that interaction extends beyond just how the moon looks. It affects how it moves. Take a moment to think about how many things on Earth feel stable, not just in a single day, but across years. The pattern of seasons, the rhythm of tides, the way the climate shifts gradually rather than unpredictably. All of these give the impression that Earth is naturally balanced, as if it simply exists in a steady state by default. But that stability is not automatic. It's the result of multiple factors working together. And one of those factors, quietly and consistently, is the moon. Not in a way that announces itself, not in a way you feel directly, but in a way that shapes the conditions you rely on every day. Start with something we've already touched on briefly, the tilt of the Earth. Our planet is tilted at about 23.5 degrees relative to its orbit around the Sun. That tilt is what creates seasons. Without it, there would be no variation in sunlight across the year, no gradual shift from winter to summer. But the important detail is not just that the Earth is tilted, it's that the tilt is relatively stable. It doesn't swing wildly from one angle to another. It changes slightly over very long periods, but it remains within a range that allows for predictable climate patterns. The moon plays a role in maintaining that stability. Its gravitational influence acts as a kind of anchor, helping to keep Earth's tilt from varying too much over time. Without the moon, that tilt could become more unstable. Not immediately, not in a way you would notice in a single year, but over thousands and millions of years, it could shift more dramatically, and those shifts would affect climate. If the tilt increased significantly, seasons could become more extreme. Hotter summers, colder winters. If it decreased, seasons could become less pronounced. Different patterns of temperature and weather. All of this would influence how life develops and adapts. Now consider how important stability is for life. Not just survival, but growth. Predictable patterns allow ecosystems to form. Plants grow according to seasonal cycles. Animals adapt their behaviour based on changes in temperature and light. Entire systems depend on the idea that tomorrow will be similar to today in certain fundamental ways. Change that predictability, and those systems are disrupted. Some species might adapt, others might not. So the moon's role in stabilising Earth's tilt is not something you notice directly, but it contributes to the conditions that make life as we know it possible. Then there are the tides. We've already explored how the moon drives the movement of the oceans, but that movement is more than just water rising and falling. It creates mixing. Nutrients are circulated, temperature differences are moderated. Marine ecosystems depend on this constant motion. In coastal areas, tidal zones create environments where life has adapted to regular changes in water level. Organisms live in conditions that alternate between submerged and exposed. And that rhythm supports a wide range of biodiversity. Without strong tides, those environments would change. The mixing of ocean water would be reduced, nutrient distribution would be different, the structure of marine ecosystems could shift, and because oceans play a major role in regulating climate, those changes could extend beyond the water, affecting weather patterns, temperature distribution, the overall balance of the planet's systems. Now, think about the length of the day. As we mentioned earlier, the moon is gradually slowing Earth's rotation. It's a very slow process, but it has been happening for billions of years. Early in Earth's history, days were shorter. The planet rotated more quickly. Over time, that rotation has slowed to the 24-hour cycle we experience now. That cycle is deeply connected to how life has evolved. Circadian rhythms, patterns of activity and rest, all shaped by the length of the day. If the day was significantly shorter or longer, life would adapt differently. And the moon has played a role in shaping that duration. Again, not in a way that is immediately noticeable, but in a way that has influenced the development of life over long periods. There's also a broader perspective to consider. The Earth-Moon system is relatively unique in the solar system. The moon is large compared to Earth. Most planets do not have a satellite of this size relative to their own mass, and that size contributes to the strength of its influence. A smaller moon would have less effect, weaker tides, less impact on axial stability, so the specific characteristics of the moon matter: its size, its distance, its mass. All of these combine to create the conditions we experience. Now, it's important to keep this in perspective. Life on Earth is influenced by many factors: the sun, the atmosphere, geological processes. The moon is one part of a large system, but it is a significant part, and its influence is continuous. It doesn't stop. It doesn't vary dramatically from day to day. It simply remains, providing a steady gravitational interaction that shapes multiple aspects of the planet. And because it is steady, it becomes easy to overlook, to assume that Earth would be the same without it. But as we explored earlier, removing the moon would change things, not in a single, dramatic moment, but through a series of adjustments that would affect the planet over time. Tides would weaken, axial stability would decrease, rotation would no longer be influenced in the same way, and those changes would ripple through the system. Now, there's also something else to consider. The relationship between Earth and the moon is not static. The moon is moving away, slowly, which means that its influence is changing over time. Again, very gradually, but over billions of years that change becomes significant. In the distant future, tides will be weaker. The interaction between the two bodies will be different. The system will evolve. But for now, we exist within a particular phase of that relationship. A phase where the moon's influence contributes to a balance that supports life. And that balance is not something you feel directly. You don't notice the moon stabilizing Earth's tilt. You don't sense the gradual slowing of the planet's rotation. You don't perceive the continuous movement of the oceans as a result of gravitational interaction. But all of these are happening, quietly, consistently, and they shape the environment in which life exists. It's another example of how the moon's presence extends beyond what we see. It's not just a visual feature in the sky, it's part of the system that defines how Earth behaves. And that system is interconnected. Changes in one part affect others, sometimes in ways that are not immediately obvious. Which brings us back to the idea of balance. The Earth-Moon system is not perfectly fixed. It evolves, it adjusts, but at this moment it exists in a state that allows for relatively stable conditions. And that stability supports life, not because it eliminates change, but because it keeps change within a range that life can adapt to. Now, when you begin to think about the moon in this way, not just as a distant object, but as an active participant in Earth's system, it becomes something more significant. Not dangerous in a direct sense, but essential in a subtle one. A quiet influence that helps maintain the conditions we rely on. And that makes the idea of the moon changing, moving closer, moving farther, or behaving differently more interesting, because those changes would not just affect the moon, they would affect Earth as well, and while such changes are not something we expect in the near future, thinking about them helps reveal how interconnected the system really is. Which leads naturally to the question, not about what the moon is now, or what it has been in the past, but about what it could become. Most of the time, the moon feels like the least threatening object you could imagine. It doesn't rush across the sky. It doesn't flare or change suddenly. It simply appears, follows its path, and disappears again, repeating that pattern so consistently that it becomes part of the background of life. So asking whether the moon could ever become a threat to Earth feels, at first, almost unnecessary. The answer seems obvious. Of course not, it's too stable, too familiar, too distant to matter in that way. But when you begin to think about what threat actually means, and how systems behave over long periods of time, the question becomes more interesting. Not because the moon is likely to become dangerous in any immediate sense, but because it reveals how much we rely on the assumption that its current behaviour will remain unchanged. Now, in the most direct interpretation, the idea of the moon colliding with Earth is extremely unlikely. The moon's orbit is stable. It is moving away from Earth, not toward it. There is no known natural process that would cause it to suddenly reverse that motion and begin falling inward. For such a scenario to occur, something significant would have to disrupt the system. A large external force, an object with enough mass passing close enough to alter the moon's orbit, or a change in the distribution of mass within the Earth-Moon system itself. These are not impossible in a theoretical sense, but they are extraordinarily unlikely, on timescales that extend far beyond anything that affects us directly. So in terms of a direct impact, the moon is not something we need to worry about. But that's not the only way something can become a threat. There are more subtle ways that involve changes to the system rather than sudden events. For example, the moon's influence on Earth is tied to its distance. As it moves away, that influence weakens. Tides become slightly less pronounced. The stabilizing effect on Earth's tilt becomes slightly weaker. These changes are extremely slow, measured over millions and billions of years. But they are part of an ongoing process. Now, in the distant future, if the moon were far enough away, its ability to stabilize Earth's tilt could diminish. That could lead to greater variations in the planet's axial tilt over time, which, as we discussed earlier, could result in more extreme or less predictable climate patterns. That wouldn't be a sudden threat. It would be a gradual shift, a change in the conditions that support life. So in that sense, the moon's absence or its reduced influence could become a kind of indirect risk. Not because the moon becomes dangerous, but because its stabilizing role changes. There's also the idea of orbital resonance. The Earth-Moon system is part of a larger gravitational network that includes the Sun and other planets. Over very long timescales, interactions between these bodies can create subtle changes in orbits. Again, not sudden, not dramatic, but present. These interactions are well understood and do not suggest any immediate instability, but they remind us that the system is not isolated. It exists within a larger context, which means that, in theory, changes elsewhere could influence it. Now there's another angle to consider, not the moon itself, but what it represents. A large body in orbit around Earth. The moon is stable because it has been part of the system for billions of years. Its orbit has settled, its interactions are predictable, but if another large object were to enter a similar orbit or pass close to Earth, the situation would be very different. The moon shows us what a stable orbit looks like, but it also highlights how much depends on that stability, because without it, gravitational interactions could become more chaotic. Now this is not a scenario we expect. There are no known objects on a path that would create such a situation, but it illustrates an important point. The moon is not dangerous because of what it is It is stable, predictable, and well understood, but it exists within a system where motion and gravity are always at work, and that system, while stable now, is not static in the absolute sense. Then there's a more immediate perspective, the moon's surface itself. While it does not pose a direct threat to Earth, impacts on the moon can occasionally be observed from Earth, small flashes of light as meteoroids strike the surface. These events remind us that the moon is constantly interacting with space, and while most of these impacts are small, they are part of a larger environment where objects move at high speeds. Earth is protected by its atmosphere. The moon is not. So in a way, the moon acts as a kind of record, a visible example of what space is like without protection. Now, consider a different kind of question. Not whether the moon will become a threat, but whether changes in the Earth-Moon system could affect how safe Earth is from other threats. For example, the moon's gravitational influence slightly affects the paths of objects near Earth. It doesn't act as a shield in the way people sometimes imagine, but it does contribute to the overall gravitational environment. Remove the moon, and that environment changes, subtly, but potentially in ways that affect how objects move through the Earth's vicinity. Again, this is not something that creates immediate danger, but it's another example of how interconnected the system is. So when you ask whether the moon could become a threat, the answer depends on how you define the question. If you mean a direct, immediate danger, something that could harm Earth in the near future, then the answer is no. The moon is stable, its orbit is well understood. There is no indication that it will behave unpredictably, but if you broaden the question, if you consider long-term changes, indirect effects, and the role the moon plays in maintaining Earth's current conditions, then the answer becomes more nuanced. The moon is part of a balance, and changes to that balance, even slow ones, can have effects. Not dramatic, not sudden, but real. Which brings us back to the central idea we've been exploring. The moon appears calm, harmless, a steady presence in the sky, and in many ways it is. But that calm appearance is supported by a system of interactions, gravity, motion, distance, all working together to create the stability we observe. And understanding that doesn't make the moon feel threatening. It makes it feel more complex, more connected, a part of a system that extends beyond what we see. And that system, while stable now, is always in motion, always evolving, even if the changes are too slow to notice directly. There's something familiar about the way the moon returns to the sky each night. You don't have to look for it very hard. Sometimes it's already there when you step outside, waiting quietly above rooftops, above trees, above everything that feels grounded and close. Other times it rises later, slowly appearing where there was only darkness before, and no matter when you notice it, the feeling is usually the same. Calm, steady, unchanging. It doesn't demand attention. It doesn't interrupt anything. It simply exists in the background the same way it always has. But now, after taking the time to move through everything we've explored, that calm presence begins to feel a little different. Not unsettling, not threatening in a sudden way, just deeper. Because the moon hasn't changed. What has changed is the way you understand it. It's no longer just a light in the sky. It's a place without air, where silence is complete and absolute. A surface where stepping from light into shadow is not just a visual shift, but a move between extreme conditions. A world covered in dust that doesn't soften over time, but remains sharp, persistent, quietly interacting with everything that touches it. A place where gravity feels lighter, but where that lightness changes how you move, how your body responds, how you maintain control. A place exposed to radiation that never announces itself, but is always there. A place where tiny particles arrive constantly from space, shaping the surface in ways that take time to notice. A place that holds the memory of its past in every crater, every mark left by impacts that happened long before humans ever looked up at it. and at the same time it's something that reaches back toward Earth. Not dramatically, not in a way you feel moment to moment, but steadily, through tides that move entire oceans, through the slow adjustment of Earth's rotation, through the stabilization of the planet's tilt, through a connection that has been shaping conditions here for billions of years. All of that exists at once, quietly, consistently, without drawing attention to itself. That's what makes the moon so interesting. Its dangers are not obvious. They are not loud or sudden. They don't come in the form of events that force you to react immediately. Instead, they exist as conditions, as properties of the environment that are always present. And because they are always present, they become easy to overlook. From a distance, the moon looks simple, a smooth disk, a steady glow, something you can glance at and understand in a moment. But understanding it fully takes more time. It requires looking beyond what is visible at first, thinking about what is happening on its surface, in its motion, in its interaction with space and with Earth. And once you do that, the simplicity fades just enough to reveal something more detailed, more layered, more real. Now, none of this means that the moon is something to fear. It doesn't change its behavior suddenly. It doesn't become unpredictable in ways that would affect you directly. It remains what it is, stable, distant, following its path. But it does mean that the calm appearance we associate with it is only part of the story. It's the part we see, the part that reaches us through light. The rest exists beyond that. In the conditions that define the moon as a place, in the processes that continue whether we notice them or not, and in the role it plays within the larger system that includes Earth. There's a quiet contrast in that. Something that looks gentle, but exists in an environment that is not. Something that feels constant, but is part of a system that is always moving, always evolving, even if the changes are slow. And maybe that's what makes the moon feel the way it does when you look at it. Not just familiar, but steady in a way that suggests continuity. A reminder that some things remain, even as everything else changes. But now that steadiness carries a little more meaning, because you know what it takes for it to be that way. You know what lies beneath the surface. You know that the silence is not empty, that the stillness is not the absence of activity, but the absence of what we're used to experiencing. And that understanding doesn't take anything away from the moon. If anything, it adds to it. It adds to. It makes it feel less like a simple object, and more like a place with its own conditions, its own history, its own role in the system we are part of. So the next time you happen to notice it, whether it's bright and full or just a thin crescent, you might find yourself looking at it a little differently. Not because it has changed, but because you have. And that quiet difference in perspective stays with you, even as everything else continues as it always has. The moon rises, the moon sets, the same face turns toward Earth, and from here it still looks calm, still looks harmless, still looks like something that simply watches over us. But now you know, it's not just watching, it's part of everything.